Macroeconomic models project artificial general intelligence will emerge between 2040 and 2050. This measurable threshold is the forecast produced by the International Futures, or IF's, platform. It operates inside a massive network of global data models tracking agriculture, economics, energy, and infrastructure across 186 countries. To calculate a realistic timeline for machine intelligence, the IF's platform relies on a quantitative index. It bypasses theoretical debates to measure actual, observable technological development. The framework categorizes AI into 3 developmental phases. Narrow AI defines today's landscape: localized, highly specific technologies constrained to single tasks, like processing language or recognizing images. Phase 2 is artificial general intelligence, or AGI. This is the threshold where a single system exhibits human-level cognitive applicability across any domain, moving between language, perception, reasoning, and planning. Phase 3 is superintelligence, characterized by an intellect whose cognitive performance vastly exceeds human capability in virtually all fields of interest. Forecasters arrive at a 2040 prediction for AGI by deconstructing the underlying variables driving the model. Mapping this trajectory requires analyzing the physical limits of hardware, the architecture of machine learning software, and the collapse of error rates in task-oriented benchmarks. Since 1965, technological forecasting has relied on a hardware baseline defined by Gordon Moore. He observed that the number of transistors on a microchip doubled every year, establishing an expectation of continuous growth in computing power. Aggregating that growth over decades suggests global computing capacity now measures between 10 to the 20th and 10 to the 21st flops. At this scale, raw hardware processing power has already rivaled high-end estimates of the human brain's computational capacity. This chart of computer processing speeds tracks transistors per chip on the top curve. Component density climbs steeply, but physical processors are encountering severe thermal ceilings. Clock speed and thermal design power have essentially flatlined since the mid-2000s. Chip manufacturers are approaching the theoretical limits of physics. Designing microscopic architecture at this scale is becoming technologically unfeasible and cost-prohibitive, capping the speed of individual processors. Because individual hardware speeds are plateauing, the predictive momentum for the IF's model must originate from an entirely different technological driver. As hardware encounters physical constraints, the acceleration of AI development has pivoted towards software architecture. The primary engine of the current forecast is deep learning. Classic AI relied on rigid, pre-programmed rules. Deep learning software bypasses those constraints by utilizing neural networks that train themselves through exposure to data, learning to detect complex patterns without human instructions. This chart projects global software revenue for systems built using deep learning. The data displays exponential growth, vaulting from roughly $100 million in 2015 to a projected $10 billion by the mid-2020s. These self-training networks are fueled by global information and communication technology penetration and a massive surge in cloud IP traffic. This infrastructure provides the massive data aggregation necessary for deep learning to evolve. The next structural leap is reinforcement learning, where machines transition into active decision-making. The system learns by attempting a specific task thousands of times in a simulated environment, optimizing its behavior with every marginal success. In 2016, a program trained for reinforcement learning defeated Lee Sedol, one of the world's top Go players. Experts previously assumed a machine victory in a game of this complexity was at least a decade away. Advanced software architecture operates untethered from individual chip limitations. Fueled by an endless stream of cloud data, it provides the exponential curve required to map a mathematically sound path toward AGI. When plotting this progress, modelers account for the AI effect. Historically, as soon as a machine successfully solves a complex problem, critics often dismiss the achievement as mere computation, moving the goalposts for what defines true intelligence. When Deep Blue defeated Garry Kasparov in 1997, the AI effect triggered a shift in standards, demanding even more complex demonstrations of intelligence to prove a machine was thinking. To maintain an empirical forecasting index, the IF's platform discards these subjective debates. This table isolates AI into 6 functional categories using a methodology called task-oriented evaluation. It breaks down cognitive concepts into defined sectors like computer vision and natural language processing. By isolating these domains, forecasters can measure quantifiable error rate reductions. They track how quickly a system learns to correctly identify objects or translate text against specific performance baselines. Forecasting the emergence of general intelligence involves tracking the compounding velocity of these highly specific narrow task improvements. Between 2010 and 2015, image classification error rates dropped from 28.2% to 6.7%, eventually plunging past the human error threshold of 5.1%. Parallel advancements occurred in natural language processing. During IBM Watson's preparation for Jeopardy, its question-answering precision, the accuracy of responses relative to those it chose to answer, doubled in just under 2 years. By 2015, deep neural networks applied to speech recognition were driving character error rates in complex languages like Mandarin down by 43%, achieving accuracy scores that surpassed native human speakers. This software optimization rapidly translated into physical space. Within 3 years, the DARPA Grand Challenge saw autonomous vehicles progress from total failure to completing 60-mile urban courses requiring real-time navigation and decision-making. Concurrently, the commercial integration of the Internet of Things provides embedded sensors across millions of physical objects. This networks vast amounts of real-world data directly back into software systems, creating a constant, automated optimization loop. While current economic impacts are largely isolated within these silos, their simultaneous compounding optimization across every domain sets the foundation for a macro-level breakthrough. Within the IF's forecast, the emergence of AGI is mathematically constrained by the rate of improvement in machine reasoning and its associated narrow technologies. This composite graph maps compounding task indices over time. The IF's platform translates disparate variables, hardware limits, software scaling, and domain benchmarks into a single ascending trendline. This unified machine IQ index tracks the system approaching a human cognitive threshold. The point of intersection provides the definitive output of the model. Based on the convergence of this data, the current path forecast estimates AGI will appear between 2040 and 2050. This forecast measures cognitive capability rather than physical form. It tracks the point where a system transitions from narrow applications to generalized problem-solving. Hitting this machine IQ threshold marks the transition of AI from a human-directed optimization tool to an autonomous agent capable of general problem-solving. The achievement of AGI triggers an immediate reaction within the forecast. The introduction of an autonomous general problem solver initiates a rapid positive feedback loop in research and development. This self-improving loop accelerates development far beyond human engineering speeds, networking into superintelligence, an intellect that exceeds human performance across virtually all domains. Tracking this accelerated feedback loop yields the final timeline. The IFS models forecast the development of true superintelligence close to the end of the current century. Tracking this trajectory identifies tangible shifts in global systems, the hollowing out of labor tasks, the optimization of renewable energy, and the restructuring of trade as automated, localized production reduces the reliance on global labor chains. The path to 2100 superintelligence remains mathematically anchored in the same narrow data models and error rate benchmarks being recorded today. Because this empirical trajectory is already compounding, global policy, industry, and governance must begin adapting to the underlying data immediately. Artificial intelligence is often treated as a philosophical thought experiment, but to understand how it might alter civilization over the next 80 years, researchers have to turn speculation into math. That is the objective of the International Futures, or IF's, Integrated Assessment Platform. It is a quantitative system designed to produce macroeconomic forecasts of AI out to the year 2100. The IF system produces dynamic forecasts for 186 countries. It maps how agriculture, energy, international trade, and education react to shifting variables across these interconnected sectors. To integrate a volatile technology into a rigid global model, researchers cannot rely on abstract definitions of intelligence. They have to operationalize AI into strictly defined, mathematically measurable indices. To build those indices, modelers divide AI into 3 rigid typological categories. The first is narrow AI. Narrow AI refers to specialized systems designed to perform only one specific task. Virtually all modern technological progress, from medical imaging to machine translation, exists exclusively within this tier. The second tier is artificial general intelligence, or AGI. This is a single system exhibiting human-level cognitive performance across any domain, including language, creativity, and long-term planning. The final tier is superintelligence. At this stage, a machine's cognitive performance exceeds human capacity in virtually all domains of interest. Establishing these boundaries allows forecasters to track progress. Each tier relies on a different set of measurable technical and economic drivers to function. Tracking progress in narrow AI is difficult because of the AI effect. When an AI successfully solves a complex problem, critics often reduce the achievement to its basic elements, claiming it is mere computation rather than intelligence. When IBM's Deep Blue defeated Garry Kasparov in 1997, the milestone was quickly dismissed. Critics argued the machine relied on brute force tactics powered by raw processing speed rather than cognitive strategy. Because the definition of intelligence constantly shifts, modelers rely strictly on task-oriented evaluations across 6 foundational technologies. They track specific performance benchmarks within these domains. For example, computer vision error rates fell from 28.2. Based on flops, current estimates indicate that global hardware processing power has already surpassed the theoretical computational capacity of the human brain. This hardware growth was historically driven by Moore's law, the observation that the number of transistors on a microchip was doubling roughly every year. This chart tracks computer processing speeds and component density. Notice the plateau in the lower data lines. Maximum clock speed and thermal power have flatlined since the early 2000s. Transistors continue to rise, but no longer yield proportional gains in speed. Because the physical scaling of hardware computation is stuttering, predicting the timeline to AGI based solely on hardware extrapolation is likely inaccurate. Facing these hardware limits, forecasters now weight software paradigms as the primary drivers of future intelligence. This chart shows forecasted global revenue for deep learning software out to 2024. Its vertical scaling stands in contrast to the flatlining hardware. Deep learning is the current dominant software approach. It mimics neural networks to detect patterns, but its success relies on exposure to massive, labeled datasets. An emerging architecture is reinforcement learning. Instead of relying on static pattern recognition, the system learns dynamic decision-making and optimization through massive trial and error. Deploying these algorithmic shifts requires massive data delivery networks. Cloud computing infrastructure and global mobile broadband penetration rates are now critical metrics in the forecast. The model's timeline for advanced intelligence now relies on this convergence, coupling advanced decision-making algorithms with real-time cloud data networks. Even highly efficient cloud-based narrow AI networks have limits. The question for forecasters is what variable is required to cross the gap to true artificial general intelligence. The friction point in current research is the absence of generalized machine reasoning and long-term planning capabilities. To account for this, the IFS model utilizes a machine IQ index. This is a theoretical index, roughly analogous to human IQ, that tracks progress across all narrow domains toward a unified score of 10. Advanced pattern recognition alone will not organically grow into AGI. A discontinuous leap in autonomous machine reasoning is mathematically required to move the index. Based on current trajectories, the IFS model generates a path forecast for intelligent technologies. It estimates machine IQ will approach human levels, leading to AGI, between 2040 and 2050. From there, the curve goes vertical, breaking the chart's top by century's end, representing superintelligence. This end-of-century spike is driven by a specific mechanism. Once AGI is achieved, intelligent machines can autonomously conduct software research, initiating a recursive, positive feedback loop that accelerates their own development. The precise slope of this mathematical timeline dictates the future of human macroeconomics, altering global productivity, the value of human labor, and international trade systems for the rest of the century. To map the future of global human development, we cannot evaluate single sectors in isolation. The International Futures Platform is an integrated assessment system that forecasts the next century across 186 countries by calculating how agriculture, demographics, and energy systems collide. Right now, those macro-level models are pointing toward a massive variable at the center of the data. Running the IF's timeline from 1950 to 2100 reveals a specific, measurable trajectory for artificial intelligence. The forecast indicates artificial general intelligence, or AGI, could appear between 2040 and 2050. By century's end, the model projects the emergence of superintelligent AI. Projecting a concrete date for generalized machine intelligence is difficult because the definition of intelligence itself is a moving target. Computer scientists call this the AI effect. As soon as researchers successfully program a machine to solve a highly complex problem, critics immediately dissect the code, declare it a calculation, and strip it of the intelligent label. We saw this clearly in 1997, when Garry Kasparov, a human grandmaster, sat down to play a computer and lost to IBM's Deep Blue. Observers dismissed the victory. They argued the machine was using brute force search tactics, executing millions of mathematical evaluations per second, rather than demonstrating actual cognition. Relying on subjective philosophical definitions of what constitutes a mind makes forecasting impossible. The IF's platform bypasses the AI effect by operating on a series of quantitative indices. To understand why this model plots AGI squarely in the 2040s, we have to deconstruct the mathematical milestones driving that timeline. The framework organizes artificial intelligence into a three-tiered taxonomy. Today, essentially all global investment, commercial application, and academic progress is concentrated strictly in this bottom tier, narrow AI. These are specialized, task-oriented algorithms designed to execute one specific function. They do not possess generalized reasoning capabilities. To model this tier, the system breaks narrow AI down into 6 measurable technological pillars. This table lists the categories, ranging from foundational research to the physical applications emanating from them. 2 heavily funded components of the space are computer vision and machine learning. The model tracks the historical performance and projected development of each of these 6 pillars, using a standardized index score, scaling from 1 up to 10. Within this mathematical framework, artificial general intelligence occurs when a single system maxes out all 6 indices simultaneously, demonstrating high-level capability across every cognitive domain. Until an algorithm achieves that perfect score across the board, it remains a specialized tool, separate from an artificial general intelligence. Historically, technology forecast relied on hardware to predict future capabilities. The logic tied artificial intelligence to raw computing power. Following Moore's law, the 1965 observation that the number of transistors on a microchip doubles roughly every year. This chart tracks computer processing speeds over several decades. It shows manufacturers hitting strict theoretical limits of space and physics. Notice how the lines tracking clock speed and thermal power plateau around 2005. Hardware-driven exponential growth is stalling. Instead, the timeline to AGI is being compressed by a different engine, advancements in algorithmic software efficiency. This chart forecasts revenue for software built using deep learning up to 2024. The sharp exponential curve illustrates the market's pivot away from localized hardware limits and toward advanced neural networks. This software expansion is accelerated by cloud computing. Shifting workloads to remote infrastructure lets developers train models on massive datasets that local physical machines could not hold. The ILF's platform keeps its 2050 timeline intact because algorithmic training and cloud infrastructure decouple the field's progress from the physical constraints of the microchip. To map this software-driven acceleration, we have to look at how these algorithms score on task-oriented evaluations over time. Plotting the historical progression of natural language processing makes the exponential trend visible. Take IBM's Watson. Between 2007 and 2009, the system's precision more than doubled, vaulting from 30% to roughly 67% in under 2 years. That compressed iteration in natural language processing gave Watson the capability to defeat a human Jeopardy champion in 2011. We can run the exact same historical evaluation for computer vision. Over a 5-year window during the Stanford AI ImageNet competition, the error rate for image classification collapsed. It dropped from over 28% down to just 6.7%. By 2015, major tech firms published algorithmic error rates of under 5%, surpassing the baseline human error threshold. When specific narrow AI technologies consistently double or triple their performance in half-decade increments, the math dictates that those individual index scales will hit their maximum well before 2050. If deep learning is advancing computer vision and language processing at this rate, it raises a question. Why does the macro model hold back the emergence of generalized intelligence for another 2 decades? We have to look back at the base taxonomy to find the bottleneck. 5 of these pillars are heavily funded and approaching peak index scores. However, the 6th category, reasoning, planning, and decision-making, lags behind. Machine reasoning requires an autonomous agent to evaluate an unpredictable environment, plan a sequence of actions, and make logical inferences under uncertainty. Deep learning software can perfectly identify a cat in a photo, but lacks the common sense to predict that the cat might jump. To bypass this limitation, researchers utilize reinforcement learning. Algorithms attempt a specific task thousands of times, mapping out optimal behaviors through rapid trial and error. We saw this in 2016 when AlphaGo defeated Lee Sedol, a champion player of Go, a game so complex it cannot be won using simple rules. A controlled board game is still a closed environment. Until developers can program an algorithm to universally simulate real-world common sense, the AGI forecast remains constrained by the development rate of this single lagging index. Returning to the century timeline finalizes the derivation. The model projects machine reasoning algorithms will compound, closing the gap with the other 5 AI categories. Between 2040 and 2050, that lagging index hits the maximum score of 10, bringing all 6 pillars into alignment. At that moment of convergence, the model defines a new unified metric, machine IQ. This is the operational equivalent to generalized, adaptable human intelligence. Once machine IQ crosses the threshold of human equivalence, we see the formal emergence of artificial general intelligence. This 2040-2050 window follows directly from the measured maturation of deep learning and the scaling capacity of cloud infrastructure. Achieving general intelligence initiates a positive feedback loop. An AGI will possess the cognitive capability to research, rewrite, and optimize its own underlying code. At that stage, the machine IQ curve detaches from human input, scaling upward at computational speeds. As a result, the model projects the final variable, the genesis of superintelligent AI near the end of the century. Treating AI as a localized tech sector is a forecasting error. The data demonstrates that AI is a foundational macroeconomic variable, one mathematically locked on a trajectory to restructure global labor, productivity, and human development for the rest of the century. Predicting the arrival of artificial general intelligence is a unique challenge because we are chasing a shifting target. There is currently no scientific consensus on what constitutes true machine intelligence. This is a result of the AI effect. When a machine solves a complex human problem, like mastering the game of Go or identifying objects in a photo, critics reduce it to mere computation. Once a task is automated, it often loses the label of intelligence entirely. Early researchers struggled by trying to build machines that could solve questions from human IQ tests. This specific focus led to a prolonged stagnation in the field throughout the 1960s and 70s. Modern forecasting avoids these philosophical debates about consciousness. Instead, it relies on raw, measurable outputs. This approach shifts the focus towards today's narrow AI systems, specialized programs that excel within very specific, isolated environments. Forecasting the singularity requires an empirical, task-oriented framework that tracks how these specialized systems are beginning to converge. The International Futures Platform, or IFAS, provides this framework. It is a quantitative macro-level system that produces dynamic forecasts for 186 countries by modeling interconnected aspects of human development. To model AGI, IFAS breaks it into 6 narrow domains: computer vision, machine learning, natural language processing, robotics, the Internet of Things, and reasoning. The platform aggregates these into a machine IQ index. A score of 10 represents parity with human capability. Current data trajectories within the IFAS model project that the global average will reach this threshold between 2040 and 2050. Proving this timeline requires working backward to examine the proximate drivers pushing these specific narrow domains toward that score of 10. General intelligence is a mathematical threshold reached when these foundational technologies converge. Raw computing power is the historical bedrock of AI development. For decades, progress followed Moore's law, the observation that the number of transistors on a microchip doubles roughly every year. Following this exponential growth, global computing capacity has theoretically surpassed the raw processing speed of the human brain, when measured in floating point operations per second, or flops. This chart shows a critical divergence. While transistors per chip continue to rise, clock speed and thermal design power have started to plateau. Chip manufacturers are reaching physical limits of space and silicon. Doubling transistor density is increasingly difficult and cost-prohibitive. There is also a massive energy gap. The human brain operates on enough power to run a dim light bulb, whereas the supercomputers needed to match its scale require enough energy to power 10,000 light bulbs. Hardware scaling alone cannot carry the industry to the 2040 threshold. A new catalyst is required to maintain the current trajectory. As hardware speed flattens, the velocity of AI development shifted towards software architecture and distributed infrastructure. The primary driver is deep learning, a framework that mimics biological neural networks. It avoids pre-programmed rules in favor of training itself to recognize patterns through exposure to massive datasets. This chart tracks the forecasted revenue for deep learning software. The rapid growth into the 2020s reflects how effectively this architecture is bypassing the limitations of raw hardware speed. Deep learning requires big data to function, but that data is too vast to exist on a single local machine. Cloud computing provides the necessary decentralized infrastructure. Whether through platforms or software as a service, the cloud supplies the continuous stream of data required. Software efficiency and global data networks are the primary drivers of the AI trajectory toward 2040. The IFS model channels these software advancements into 6 trackable categories of narrow AI technology. This matrix operationalizes the forecast, focusing on computer vision, machine learning, natural language processing, and robotics. Progress is measured by task-oriented evaluation. The model tracks rising precision and falling error rates in commercial products, from medical imaging to automated customer support. Billions in private investment accelerate these domains far beyond the pacing of traditional academic research. These pillars progress asynchronously. Some technologies are nearing human parity today, while others remain years behind. Mapping independent industry benchmarks is the most reliable way to plot a trajectory toward general intelligence. Once a technology integrates with massive cloud-based data networks, the system's previous limitations vanish, and its task-specific error rates begin to completely collapse. For instance, the precision of IBM's Watson, its ability to correctly answer questions relative to those it chose to answer, more than doubled in just 2 years. Computer vision has seen similar gains. In the Stanford ImageNet competition, image classification error rates fell by a factor of 4 in just 5 years. However, the model identifies a single bottleneck. While vision and language processing are scaling, this final row, reasoning, planning, and decision-making, shows very limited modern applications. Pattern recognition is currently exponential, but the capacity for machines to perform abstract reasoning or set autonomous goals remains in a nascent, unproven state. The 2040 timeline is gated entirely by the developmental velocity of this single reasoning pillar. The IFS model tracks these 6 converging domains. Their advancement contributes to a rising machine IQ score. Reaching an index of 10 signifies AGI is available, matching human capability. Based on momentum, this threshold is crossed between 2040 and 2050. This is the current path forecast. Slower or faster scenarios depend on future corporate investment and the continued build-out of global data infrastructure. The 2040 horizon is an empirical projection based on commercial momentum, moving AGI out of the realm of science fiction and into actionable policy timelines. Crossing the 2050 threshold establishes a new foundational baseline for development. AGI systems can now optimize their own software and solve hardware constraints. This creates a recursive feedback loop, entirely removing human research bottlenecks. This self-improving cycle drives the machine IQ score towards superhuman levels across every field of interest. Based on this trajectory, the IFS platform forecasts the emergence of superintelligent AI near the end of the current century, around the year 2100. The singularity is the relentless mathematical accumulation of narrow technological systems compounding over time. The International Futures Platform, or IFS, processes an enormous volume of macroeconomic data to produce dynamic, integrated forecasts for 186 countries. Its primary projection places the emergence of artificial general intelligence, or AGI, between 2040 and 2050. By the year 2100, the model projects the arrival of superintelligence, systems that exceed human cognitive performance across all domains. This timeline is a rigorous, integrated systems forecast built entirely on measurable inputs, grounded in current technological trajectories. To validate these dates, we have to look past the top-line projections and deconstruct the underlying methodology driving the models. The platform calculates this timeline by tracking 4 core drivers: hardware capabilities, software architecture, global cloud computing volume, and information and communication technology penetration. Forecasting generalized intelligence requires treating cognitive capability as a measurable output, one constrained entirely by physical and digital supply chains. All artificial intelligence development relies on a baseline of physical hardware and raw computing capacity, measured in floating point operations per second, or flops. This graph shows the historical progression of Moore's law. For decades, raw computing capacity scaled exponentially simply by doubling the number of transistors on a microchip. But this multi-line chart comparing performance metrics reveals a physical reality. We are hitting the thermal and spatial limits of silicon. While the number of transistors per chip continues its upward trajectory, maximum clock speed and thermal design power flatlined in the early 2000s. Intel's own industry models indicate that continuing to double transistor counts in the near term is becoming cost-prohibitive and heavily restricted by the laws of physics. To understand the raw processing gap, compare modern supercomputers to the human brain. The best supercomputers can process data faster than the brain, but the energy discrepancy is massive. Supercomputers require enough energy to power tens of thousands of light bulbs, while the human brain operates on the equivalent of a single dim bulb. Because of these physical and thermal constraints, the 2040 AGI forecast cannot rely on infinite hardware scaling. The intelligence gap has to be closed by radical shifts in software architecture. Facing flatlining clock speeds, the tech industry pivoted heavily toward deep learning. Instead of relying on pre-programmed rules, these algorithms train themselves by detecting patterns through massive exposure to data. This stacked bar chart illustrates the economic reality of that pivot. Capital influx into deep learning software exploded starting in 2015 and is scaling toward 2024. This shift was accelerated by cloud infrastructure. Developers can now decouple massive data processing requirements from local, firmly limited hardware and push it off-site. Cisco projected a 30% compound annual growth rate, with annual global cloud traffic reaching 14.1 zettabytes by 2020. That networked volume of cloud traffic creates the raw big data necessary to feed and train modern deep learning models. This architecture enables reinforcement learning. Systems bypass human programming entirely, iterating through thousands of simulated failures and successes to optimize their own behavior. The global volume of networked data and cloud computing capacity has replaced the physics of the microchip as the primary constraint on AI development speed. This table details how the IFS framework evaluates the current landscape. It breaks artificial intelligence down into highly specialized narrow AI technologies, like computer vision and natural language processing. The industry has shifted toward a task-oriented evaluation. Intelligence is measured strictly by performance benchmarks on specific, isolated problems, rather than philosophical definitions. Take machine learning. Between 2007 and 2009, the precision of IBM Watson in answering complex Jeopardy questions more than doubled. In the domain of computer vision, error rates in the Stanford ImageNet competition plummeted from 28.2% to 6.7% in just 5 years. By 2015, Microsoft's image recognition achieved an error rate of 4.94%, officially crossing the human error threshold of 5.1%. Natural language processing saw similar error reductions, drastically improving capabilities in both speech recognition and real-time machine translation. The IFOS model takes these isolated, rapid improvements across disparate fields and synthesizes them to extrapolate a forward-looking growth rate for generalized machine IQ. The 2040 timeline is a mathematical extrapolation. The model assumes that the compounding exponential curves of these distinct narrow tasks will inevitably converge into general intelligence. Even with narrow AI metrics already advancing exponentially and crossing human thresholds, the IF's model holds its AGI declaration until 2040. Looking closely at the specific categories of narrow AI reveals a single lagging metric preventing the system from achieving general intelligence. Current deep learning is exceptional at pattern recognition, but it lacks generalized machine reasoning, the capacity to plan, infer, and adapt in unpredictable environments. The emergence of artificial general intelligence is strictly and mathematically constrained by the rate of development in this specific reasoning subfield. Once this reasoning bottleneck is finally cleared mid-century, the system hits a tipping point, initiating a recursive positive feedback loop. An AGI system will immediately begin directing its own research, writing its own code, and designing better hardware architectures, drastically compressing the time between iterations. That recursive self-improvement is precisely why the IFAS model forecasts superintelligence, an intellect vastly exceeding human limits, arriving shortly after AGI, before the year 2100. Forecasting AGI requires mapping the moment when hardware limits, expanding cloud infrastructure, and the systematic mastery of cognitive reasoning collide. The International Futures Platform, a macro-level integrated assessment system used to model global human development, pinpoints a specific window for the emergence of artificial general intelligence between the years 2040 and 2050. Most discussions about general AI rely on science fiction tropes. To determine when this technology might actually arrive, we have to look past the myths and toward the rigid geometric data structures of quantitative models. This forecast is generated by the International Futures, or IF's, platform at the University of Denver. It is a system that produces dynamic forecasts for 186 countries by modeling interconnected sectors like agriculture, economics, demographics, and international politics. If a macro-level model projects artificial general intelligence arriving within the next few decades, we need to identify the physical metrics and historical benchmarks that justify such a precise timeline. Moving the conversation from philosophical speculation to quantifiable parameters is the only way to accurately track and prepare for a shift of this scale. To understand the 2040 result, we are going to work backward to reverse engineer the methodology of the IFS model. The process begins with a strict taxonomy that separates AI into three distinct tiers: narrow AI, general intelligence, and superintelligence. The first quantitative pillar of the forecast involves tracking the physical limits and scaling potential of computer hardware. The second pillar analyzes the growth of specific software architectures, particularly those capable of self-directed learning. The third pillar provides the data baseline, using hard mathematical results from task-oriented performance benchmarks. Deconstructing these three pillars transforms the arrival of AGI from a vague prediction into a measurable parameter of technological progress. The first tier of the model is narrow AI. These are specialized systems designed to perform exactly one task, such as identifying a specific object in a photograph or translating a block of text. The second tier is artificial general intelligence, or AGI. This describes a single system that exhibits human-level cognitive ability across all domains, including reasoning, creativity, and planning. Narrow AI relies on 6 foundational technologies: computer vision, machine learning, natural language processing, IoT, robotics, and reasoning. Today's breakthroughs exist solely within these confines. The bridge to AGI depends on machine reasoning, currently the most limited category, restricted to structured logic problems. Because this skill is foundational for general intelligence, the entire 2040-2050 timeline is mathematically gated by how quickly we can develop machines that reason rather than just recognize patterns. Reasoning requires physical infrastructure. To build the model, we have to look at the hardware limits that dictate how much compute is available to these algorithms. For decades, hardware expectations were set by Moore's law. In 1965, Intel co-founder Gordon Moore observed that the number of transistors on a microchip doubled roughly every year, creating an exponential growth trajectory. However, we are reaching the theoretical limits of physics. As this chart shows, the number of transistors per chip began to plateau in the early 2000s, making traditional scaling increasingly difficult and expensive. The IFES model accounts for this plateau by shifting its focus from individual chips to global calculation volume, measured in flops, or floating point operations per second. Global computing capacity is currently estimated at 10 to the 21st flops. This puts raw machine volume well within the range of the human brain, which is estimated to operate between 10 to the 16th and 10 to the 25th flops.
But there is a massive efficiency gap. The human brain requires only enough energy to power a dim light bulb, while the most powerful supercomputers consume enough electricity to power 10,000 light bulbs. Because of these energy constraints, the path to AGI relies on a massive expansion of global cloud infrastructure, rather than the power of individual localized machines. Hardware is only the engine. The model also requires software architectures to utilize that raw power. The most significant shift has been deep learning, software that mimics biological neural networks. Unlike traditional programs, these systems are not given a set of rules. They learn by detecting patterns within vast amounts of data. This revenue explosion is a key driver for research. Market spending on deep learning software is projected to scale from just $100 million in 2015 to over $10 billion by the mid-2020s. The model also factors in reinforcement learning. Here, machines move from passive pattern recognition to active decision-making, learning through a continuous feedback loop of trial, failure, and success. This method reached a landmark milestone in 2016 when the program AlphaGo defeated world champion Lee Sedol in the game of Go. Because Go is too complex for rules-based programming, experts believed a machine victory was still a decade away. This breakthrough proved that learning by doing could simulate a form of computational intuition. In the IFAS model, this transition towards self-teaching algorithms is the critical catalyst needed to eventually automate generalized human reasoning. To track the speed of this progress, we have to navigate the AI effect. This is the tendency for a machine's achievement to be dismissed as not true intelligence the moment the problem is solved. To maintain objectivity, the IFE platform ignores these shifting goalposts and relies on task-oriented evaluations, measuring the mathematical collapse of error rates over time. In computer vision, object identification error rates plummeted from 28.2 to 6.7% in 5 years. Simultaneously, natural language processing precision climbed, with IBM Watson's accuracy doubling in 2 years. Machine translation showed similar trajectories, significantly improving over 4 years. The IFES model extracts these narrow performance metrics, treating them as foundational vectors of technological momentum. The forecast for AGI is not a guess. It is the mathematical extrapolation of these error rates as they approach zero across multiple domains. The platform synthesizes physical compute limits, software scaling patterns, and benchmark data into a single unified output. This aggregated metric is the Machine IQ Index, an index score that allows for the comparison of machine capability against human standards. Projected onto the global timeline, this composite trendline crosses the human equivalence threshold between 2040 and 2050. Once achieved, an AGI triggers a self-reinforcing feedback loop, contributing to its own research. This sparks an intelligence explosion, forecasting superintelligence near the century's end. It is important to note that this entire projection fails if isolated proficiencies in computer vision or language cannot be successfully integrated into general reasoning. The 2040-2050 window is not a certainty, but a probabilistic output based on the current path of technological development. Establishing this rigorous baseline is essential for policymakers. It provides a framework to prepare labor markets and economic systems for the arrival of generalized intelligence. In 2022, researchers published a peer-reviewed paper detailing a quantitative forecast. Artificial General Intelligence, or AGI, will emerge between the years 2040 and 2050. AGI requires a machine to exhibit human-level cognitive performance across all domains. This is a stark contrast to the narrow, highly specialized AI applications we use today. To calculate the timeline to AGI, the researchers utilized the International Futures, or IF's, integrated assessment platform.
Predicting the exact arrival of a technology that does not currently exist invites obvious skepticism. Yet the IF's platform models a precise progression. Our current era of narrow AI, AGI appearing between 2040 and 2050, and eventual superintelligence. To understand this 2040 window, we must examine hardware limits, cloud architecture, and shrinking algorithmic error rates. The International Futures Platform is a quantitative macro-level system that produces dynamic forecasts for 186 different countries. It processes millions of data points across deeply interconnected global sectors, measuring variables like energy infrastructure, demographic shifts, international politics, and economics. Within this massive architecture, the model quantifies AI development by assigning a numerical index score out of a maximum of 10. In this system, AGI does not appear as a sudden spark of digital consciousness. It is the mathematical byproduct of specific, measurable technological developments converging at a critical threshold. Raw computing power has driven artificial intelligence research for decades. This graph from 1965 shows Gordon Moore's famous observation: the number of transistors on a microchip doubles roughly every year. But semiconductor manufacturers are now hitting the constraints of physics. A hard spatial limit dictates how densely we can pack components onto a piece of silicon. We can see those physical limits in this chart mapping recent hardware development. Notice the plateau occurring right after the early 2000s in maximum clock speed and thermal design power. Because individual chip speed is flattening, researchers evaluate total global computing capacity using flops, or floating point operations per second. By 2015, experts estimated that total global computing capacity had reached an astonishing 1.5 times 10 to the 21st power flops. High-end estimates of the human brain place its raw calculation capability between 10 to the 18th and 10 to the 25th power. The hardware has matched the biological calculation speed, but the efficiency gap remains massive. The fastest supercomputers require the energy of 10,000 light bulbs to operate, while the human brain runs on the energy of a single dim bulb. With total processing power crossing the human baseline while individual chip speeds stall, the timeline for AGI depends almost entirely on advances in software. That software advance is driven by deep learning, algorithms designed to mimic biological neural networks, allowing machines to recognize patterns and train themselves without relying on pre-programmed instructions. This stacked bar chart maps the financial validation of that technology. You can see the forecasted revenue for deep learning software accelerating sharply, projecting past $10 billion by the mid-2020s. Deep learning algorithms are powerful, but they share a major vulnerability. They break down unless they are continuously exposed to vast amounts of fresh data. The infrastructure sustaining this data requirement is global cloud computing. Cloud networks crowdsource information from billions of devices, creating the training environment necessary for algorithms to improve. To quantify that scale, telecommunications forecasts projected global cloud IP traffic to reach 14.1 zettabytes annually by 2020. The AGI timeline relies entirely on this synergy. Self-training software algorithms only work when paired with an exponentially growing zettabyte-scale data infrastructure. Even with massive data pipelines and capable software, intelligence remains a subjective concept. The IFAS model requires a measurable way to track forward momentum. This table outlines the model's solution: task-oriented evaluation. It tracks the reduction in error rates across 6 narrow AI pillars: computer vision, machine learning, natural language processing, robotics, the Internet of Things, and reasoning. We can trace this progress historically. In 1997, IBM's DeepBees system successfully defeated human grandmaster Garry Kasparov using early machine learning and raw calculation. Today, the error rates in these pillars are collapsing rapidly. In the Stanford ImageNet competition, computer vision classification error rates plummeted from 28.2% down to 6.7% in just 5 years. Natural language processing made similar leaps. Programs like Baidu's Deep Speech 2 achieved a 5.8% error rate, recognizing English and Mandarin character patterns more accurately than human listeners. But one crucial pillar still lags significantly behind the others: the complex realm of machine reasoning, forward planning, and autonomous decision-making. Unlike identifying a cat in a photo or translating a sentence,
Generalized machine reasoning is highly complex to evaluate mathematically and has very few modern applications. This single lagging category acts as the pacing mechanism for the entire IIF's forecast. AGI cannot materialize until the error rates in machine reasoning compress at the exact same speed as vision and speech. To forecast the future, the model aggregates the data from all 6 of these narrow technological pillars. It combines their individual trajectories into a single, unified metric called the Machine IQ Index, tracking the parallel convergence of the technologies. The model projects that as the machine reasoning algorithms catch up to the other 5 pillars, this combined machine IQ score will approach a perfect 10 out of 10. The mathematics point to a specific intersection. That perfect index score will be reached between 2040 and 2050. AGI is therefore modeled as a synthesis. It is the exact point when specialized, narrow systems achieve interoperability and master human-level reasoning simultaneously. Once the model crosses the 2050 threshold, the parameters for computer science change completely. Reaching AGI triggers a positive feedback loop. An artificial general intelligence will possess the cognitive capacity to analyze, iterate, and rewrite its own source code. Human researchers are restricted by biological cognitive limits and slow hard rate supply chains. An AGI optimizing itself faces none of these constraints. This loop outputs what is known as superintelligent AI, an intellect that drastically exceeds human cognitive performance across virtually every domain. Driven by this unconstrained self-improvement cycle, the IFS platform projects superintelligence will emerge near the end of the 21st century. The path to a superintelligent future relies entirely on the measurable, methodical compression of algorithmic error rates occurring right now.
To project the future of artificial intelligence, researchers at the Pardee Center built a comprehensive forecast. Their model projects AGI will emerge between 2040 and 2050 and extends to the end of the century, pointing to superintelligent AI. Building a macro-level forecast like this presents a unique challenge. Mapping the timeline requires measuring progress, but traditional philosophical definitions of human intelligence are subjective and shift over time. This creates the AI effect. When a machine masters a task, critics immediately deconstruct the achievement, categorizing it as mechanical computation rather than actual intelligence. Because of this effect, the standard for what constitutes true intelligence remains a moving target. This instability makes it a poor metric for a rigorous statistical forecast. To build a reliable timeline, the International Futures Platform, or IFAS, bypasses this moving target entirely. Instead of debating whether a machine achieved a spark of consciousness, the model avoids philosophical definitions. It uses a mechanism called operationalization. This process takes abstract concepts and grounds them in hard, quantifiable mathematics. The system measures a machine's ability to complete specific, practical objectives, moving past the debate over consciousness to focus on hard, task-oriented proxies. By quantifying the rate of progress across a series of distinct, narrow AI subfields, forecasters can build a mathematically grounded projection of the AGI timeline. Predicting the emergence of AGI relies on meticulously tracking the convergence of these discrete, measurable computational tasks. For decades, the baseline constraint for modeling artificial intelligence was raw computing power. Today, global computing capacity operates near the high-end estimates of the human brain, processing roughly 10 to the 20th power floating point operations per second. But relying on exponential hardware growth to predict AGI is no longer viable. Chip manufacturers are hitting the physical and thermal limits of silicon. This chart displays historical microprocessor trends. Notice the clear plateauing of both clock speed and thermal design power starting in the early 2000s. Moore's law is stuttering. Confronted with these physical limits, the tech industry redirected capital investments away from raw transistor density. The proximate driver of AI development shifted from hardware to software, specifically to deep learning architectures. Compare that stagnating hardware chart to this forecast of deep learning software revenue. The data shows an exponential upward spike from 2015 through the mid-2020s. These modern systems differ from early AI.
Rather than executing rigid rules, they learn and adapt by mining massive datasets hosted on global cloud infrastructure. The AGI timeline is no longer gated by our ability to build a physically larger electronic brain. The constraint is how efficiently we can organize the software systems running on existing hardware. To map this explosion in software capability, the IFES platform disaggregates AI into 3 specific tiers: narrow, general, and superintelligent. Currently, almost all commercial investment and technical progress is confined entirely to the narrow AI tier. To quantify this progress, the Party Center relies on a specific architectural framework. It starts by tracking 3 distinct sensory and communicative capabilities: computer vision, machine learning, and natural language processing. Next, it monitors 2 physical and systemic domains: robotics and the Internet of Things. Finally, the framework requires a central, unifying capability to complete the model: machine reasoning. Within the IFEF's model, each of these 6 domains is assigned an index score from 1 to 10, allowing forecasters to track technological maturity continuously. By fragmenting the idea of intelligence into 6 measurable indices, researchers transform an unpredictable technological leap into a manageable engineering timeline. To score those indices, the model employs a standard known as task-oriented evaluation. Progress is measured exclusively against a system's ability to successfully complete specific, verifiable outcomes. Take the computer vision node as an example. Between 2010 and 2015, error rates in the Stanford ImageNet classification competition fell from over 28% down to just 6.7%. Shortly after, image recognition algorithms crossed the 5.1% error threshold, surpassing human accuracy levels. A similar acceleration is visible in the natural language processing node. In just a 3-year span, the precision of commercial question-answering systems like IBM's Watson more than doubled. During a similar time frame, NIST benchmark scores for Chinese to English machine translation showed steady gains against human baselines. This creates a clear mathematical function. As these real-world error rates drop toward 0, the corresponding index score for that domain climbs toward 10. Right now, technologies rooted in computer vision, natural language processing, and machine learning are doubling or even tripling their performance every 5 years. These compounding advances are pushing 5 of the 6 narrow AI domains rapidly toward their maximum index scores. The data shows sensory systems and pattern-matching AIs are effectively solved problems on a macro timeline. They are not the variables holding back general intelligence. There is a single variable that refuses to scale exponentially: machine reasoning. Machine reasoning differs from basic pattern recognition. It requires formulating plans, weighing abstract logic, and executing complex decisions in environments defined by extreme uncertainty. Achieving AGI requires more than just stacking natural language and vision algorithms. A system needs this central, autonomous decision-making capacity to bind those sensory inputs into a coherent, general intellect. Because of this, the model operates under a strict constraint. The timeline for AGI emergence is dictated by the rate of improvement in this reasoning node. The system defines the threshold explicitly. AGI triggers only when the aggregate index reaches 10 across all 6 approaches simultaneously. The 2040 forecast represents a statistical projection of when machine reasoning matures enough to unify with machine perception. Once that final reasoning node reaches maturity and all 6 indices hit a score of 10, the behavior of the model shifts. At this point, the IIF's platform aggregates the collective scores of these 6 disparate subsystems, from language to robotics, into a unified machine IQ index. This score allows modelers to assess synthetic performance across all cognitive domains against human IQ benchmarks. Projecting the timeline forward, the machine IQ index is expected to mathematically intersect with baseline human capability between 2040 and 2050. Hitting that threshold acts as the catalyst for a new structural dynamic. It initiates a recursive, positive feedback loop within technological research and resource optimization. Once AGI is achieved, the AI systems themselves take over the labor of subsequent AI development. They bypass human cognitive limits and biological processing speeds entirely. When this feedback loop is mapped on to the remainder of the century, the trajectory shifts from linear engineering to an accelerating, compounding result of machine-led optimization.
Reaching general intelligence requires decades of grueling engineering to solve the reasoning bottleneck. But once that barrier is cleared, the transition to superintelligence will follow an accelerating, self-sustaining path toward the end of the century. Predicting the arrival of artificial general intelligence requires moving past philosophical speculation and science fiction. To understand when it will emerge, analysts must rely on rigorous, quantitative modeling. This chart models a timeline from 1950 to 2100. By tracking historical data, the plotted curve for machine IQ projects that general artificial intelligence will become available specifically between 2040 and 2050. Intelligence does not arrive as a single spontaneous flash of insight. Forecasting it requires a macro-level system capable of tracking complex, interconnected variables over decades. To build this timeline, researchers use the International Futures, or IFIS, platform. It is an integrated assessment model designed to produce dynamic macroeconomic and developmental forecasts for 186 countries. But because general intelligence does not exist yet, the model cannot track it directly. The IIF's platform has to operationalize the concept of intelligence, breaking it down into specific historical components that can be tracked and measured. The foundation of this model relies on splitting the idea of a monolithic artificial intelligence into narrow, task-oriented subdomains. The progress of each of these individual subdomains depends entirely on physical constraints, specifically the development of computing hardware capabilities and the design of underlying software architectures. By evaluating the historical performance benchmarks and the physical limits of these exact subdomains, the mathematical path to a 2040 arrival date becomes visible. We begin with the physical constraints. Historically, global computing capacity, measured in floating point operations per second, or FLOPS, has grown exponentially. Current estimates place global hardware processing power well beyond the computational capacity of the human brain. This chart shows the number of transistor components per chip plotted on the log scale between 1959 and 1975. This linear exponential upward slope illustrates Moore's law, the decades-long trend of doubling transistor counts that served as the primary engine for early AI progress. But chip manufacturers are hitting physical limits. In this chart, the curves for clock speed and thermal design power plateau sharply under the stuttering header. To maintain baseline growth despite flatlining speeds, manufacturers must rely on the increasing complexity of placing more transistors per chip. Because raw hardware scaling is stuttering, the development timeline for general intelligence would stall completely if physical processors were the only driver of progress. To bypass this physical bottleneck, the industry has pivoted toward algorithmic efficiency. Software architectures are now doing the heavy lifting. This acceleration is primarily driven by deep learning and reinforcement learning frameworks. This chart displays the forecasted revenue for software built using deep learning. It tracks an exponential explosion in commercial investment and market value, approaching $10 billion by the mid-2020s. Deep learning frameworks allow systems to train themselves to detect patterns and make decisions without rigid pre-programmed rules. But to do this effectively, they require massive, distributed datasets to learn from. The infrastructure necessary to feed these massive datasets into the algorithms is provided by the rapid expansion of distributed cloud computing networks. The convergence of advanced deep learning architectures and robust cloud infrastructure has replaced Moore's law as the primary engine pushing the field toward AGI. Despite this software boom, all current progress remains strictly confined to narrow AI, specialized systems designed to execute singular tasks. This table outlines the exact taxonomy used by the IFIS platform. Focusing on the type and description columns, the model establishes 6 distinct categories to track: computer vision, machine learning, natural language processing, robotics, the Internet of Things, and reasoning. Computer vision and natural language processing function as the perceptual domains. They are the mechanisms for machines to ingest visual and text data, interpret it, and interact with humans. Robotics and the Internet of Things operate as the execution domains. These allow machines to physically interact with their environments and optimize physical networks. These pillars operate in strict separation. High performance in image recognition offers zero competence in navigating a physical space or parsing language.
To accurately forecast general intelligence, the IIF's platform must isolate these 6 silos. It measures their specific historical performance rates completely independently before attempting to combine them. The model evaluates these silos using task-oriented evaluation. It takes qualitative AI milestones, like winning at chess or translating documents, and converts them into a quantifiable index score ranging from 1 to 10. This chart graphs the Stanford AI ImageNet competition data. In just 5 years, object classification error rates experienced a 4-fold drop, plummeting from 28.2% down to 6.7%. We see similar acceleration in natural language processing. IBM Watson more than doubled its response precision in under 3 years, while Baidu's deep speech software reduced its character error rates by 43%. Yet, these rapid perceptual advancements contrast sharply with a severe lack of progress in the 6th pillar, general machine reasoning, planning, and decision-making. Generalized decision-making breaks down when machines are placed in highly dynamic, unpredictable real-world environments without pre-programmed rules. The sheer density of variables in an organic setting completely overwhelms the system's capacity to plan its next action. The 2040 forecast is strictly gated by this bottleneck. While the perceptual and execution domains are scaling rapidly, general intelligence cannot emerge until the constraint on machine reasoning catches up. This graph illustrates how the IIF's platform remerges the historical trajectories of all 6 distinct narrow AI pillars. They are aggregated into a single unified machine IQ index score, tracking upward toward a dashed horizontal threshold representing human equivalence. The model calculates a distinct mathematical convergence point. It forecasts that these aggregated scores will breach the human equivalence threshold specifically between 2040 and 2050. Once machine IQ hits superhuman levels, a secondary forecast activates. Positive feedback loops in algorithmic self-improvement trigger an asymptotic spike in capability, leading to the emergence of superintelligent AI near the end of the current century. The emergence of general intelligence is modeled here as a strict mathematical convergence of specific measurable capabilities, rather than a spontaneous technological awakening. The ultimate utility of this framework lies in what strategists can do with the variables. Analysts using the platform can manipulate specific proximate drivers. By adjusting hardware stuttering limits or altering the investment growth rate of deep learning software, they can test faster or slower alternative timelines for AGI. Because IIF's is an integrated assessment platform, shifting the AI timeline cascades directly into models of global human development. Users can track exactly how a delay or acceleration in AGI impacts global economic productivity, shifts in labor displacement, and international trade patterns. By disaggregating artificial intelligence into a quantitative framework, analysts can replace speculative anxiety with a rigorous, testable tool for global macro forecasting. A global forecasting system projects the emergence of artificial general intelligence between the years 2040 and 2050. This timeline is the result of calculations performed by the International Futures, or IFAS, Integrated Assessment Platform. It is a quantitative macro-level model that tracks 186 countries across 13 interconnected sectors, including economics, demographics, and energy systems. The IFAS system treats AI development as a measurable input that interacts directly with global technological and political infrastructure. By integrating machine intelligence into a strict macroeconomic framework, the model frames the emergence of AGI as a concrete, timeline-bound infrastructure problem. The forecast utilizes a specific taxonomy of 3 stages. The base phase is narrow AI, specialized systems designed to perform single, isolated tasks, like image recognition or translation. The second phase is AGI, or artificial general intelligence, representing a system capable of human-level cognitive performance across any and all domains. The final phase is superintelligence, exceeding human capability in all areas. To bridge these stages, the IFAS model employs a mathematical metric, the Machine IQ Index. The model identifies human equivalence at a baseline score of 10. Crossing this triggers AGI. Forecasting the year 2040 is a calculation of the physical and digital drivers pushing this machine IQ score toward that threshold. This log-scale graph tracks the historical engine of AI development. the exponential growth of computing hardware and transistor density. But chip manufacturers are reaching the boundaries of space and physics. This chart highlights the stuttering of traditional hardware progress. Since the mid-2000s, the trajectories for clock speed and thermal design power have flattened, even as the total number of transistors continues to rise. Global computing capacity, measured in floating point operations per second, has reached a level where top-tier supercomputers theoretically match the raw processing power of the human brain. However, an efficiency gap remains. Biological brains operate on the power required for a dim light bulb, while supercomputers require tens of thousands of times more energy for similar output. If hardware were the only variable in the machine IQ index, the timeline to AGI would be extending. The model remains on track because of compensatory acceleration in other areas. That acceleration is driven by algorithmic software breakthroughs and distributed cloud infrastructure. Deep learning represents a critical pivot toward neural networks that train themselves through exposure to data, rather than relying on pre-programmed rules. This bar chart displays the massive capital investment currently fueling this software paradigm. Revenue for software built with deep learning is projected to scale from $100 million in 2015 to over $10 billion by the mid-2020s. This has led to the rise of reinforcement learning, where algorithms learn decision-making through millions of iterative trial-and-error simulations. In 2016, a reinforcement learning program called AlphaGo defeated Lis et al. This victory demonstrated that machines could outmaneuver humans in tasks requiring complex, non-rules-based logic. Cloud computing supports these algorithms by providing the massive, decentralized data troves required for training, effectively bypassing localized hardware limits. The exponential growth of cloud data and self-training algorithms has overridden the decay of Moore's law, keeping the 2040 forecast on schedule. While software capabilities are expanding, all current progress is strictly contained within the task-oriented framework of Marrow AI. The IF's platform models 6 technological pillars: computer vision, machine learning, natural language processing, robotics, the Internet of Things, and reasoning. In computer vision, image classification error rates plummeted by a factor of 4 over 5 years. Machine vision algorithms reached an error rate of 4.94%, surpassing the human threshold. Within natural language processing, virtual assistants have shown similar rapid accuracy improvements in parsing human speech and intent. IBM Watson's victory on Jeopardy provided an early benchmark for this precision, showcasing high-speed data retrieval and language parsing under pressure. These pillars are achieving superhuman benchmarks, but they remain deeply siloed. The transition to general intelligence is restricted by the lack of a unifying cognitive architecture. The lacking pillar of the IF's taxonomy is reasoning, planning, and decision-making. Machine reasoning is the capacity to apply logic, make inferences, and navigate ordinary, unprogrammed situations in dynamic environments. Current deep learning models require massive datasets to recognize specific patterns, but they struggle when a situation requires common sense or navigating unexpected context shifts. The AGI threshold in the IIF's model is a function of the forecasted rate of improvement in this reasoning pillar. Based on the compounding trajectories of private investment and cloud networking, the model projects this reasoning gap will close within roughly 2 decades. The transition to general intelligence occurs when machines possess the reasoning capacity to synthesize these siloed domains autonomously. In the middle of this century, the machine IQ index clicks over to 10. The model predicts that this threshold triggers a positive feedback loop in research and development. A general AI would possess the capability to engineer, rewrite, and optimize its own code faster and more efficiently than human researchers. This feedback loop drives the secondary IFO's forecast. Superintelligence is projected to arrive before the end of the century. The window between AGI and superintelligence is brief, a period defined by a compounding acceleration of technology that humans no longer drive. This forecast details an imminent geopolitical and economic reality, a massive shift of economic value add away from human labor and toward automated systems. This shift creates secondary ripple effects, fundamental restructuring of international trade patterns, localized production capacities, and optimized renewable energy grids. The 2040 timeline represents less than a single generational working cycle for global institutions to adapt to these shifts. Integrating the AGI timeline into macro-level models is the baseline requirement for navigating an automated global economy.
Current quantitative path forecasts point to a window between 2040 and 2050 for the emergence of artificial general intelligence. According to a macro-level projection developed by researchers at the University of Denver, this is the decade when machines match broad human cognitive capability. That projection relies on the International Futures Integrated Assessment Platform. This is a quantitative system that models global human development by calculating the continuous interactions between agriculture, energy, economics, demographics, and technology. Using this platform, researchers map out two distinct destinations. The first is AGI, representing general cognitive equivalence to humans. The second, positioned toward the end of the century, is superintelligence, an intellect that exceeds human cognitive performance across virtually all domains. Forecasting a technological event that has not yet occurred presents a challenge for traditional modeling. We cannot measure the performance of a machine that does not exist. To solve this, the International Futures methodology avoids predicting isolated software breakthroughs. Instead, it builds the forecast by disaggregating intelligence into a series of measurable foundational drivers that can be tracked through historical and current data. These proximate macro drivers include the physical constraints of hardware computing, the evolutionary path of software algorithms, and the total data capacity of our global cloud infrastructure. AGI is therefore modeled as a predictable threshold. It occurs once these specific technological variables hit a critical, unified density. Every single calculation requires physical space. The baseline constraint dictating all artificial intelligence potential is hardware processing power. For decades, hardware scaling relied on Moore's law. Proposed in 1965, it observed that the number of transistors on a microchip doubled roughly every year, establishing a reliable trajectory for computing power. This chart tracks computer processing metrics over time. The upper solid black line confirms the historical volume of transistors per chip, reliably scaling upward. But chip manufacturers are now reaching the physical limits of silicon, causing hardware development to stutter. The lower trend curves reveal the constraint. Thermal design requirements and complex spatial physics have caused maximum clock speeds to flatten since the early 2000s. Because of these architectural limits, raw clock speed is no longer the primary metric for scale. The industry standard for estimating global computational capacity is now flops, or floating point operations per second. Estimates of human brain computing power range broadly from 10 to the 18th to 10 to the 25th flops. Based on the lower end of those estimates, current supercomputers can process data in greater volumes and with more speed than human biology, yet the energy efficiency gap remains significant. The human brain operates on enough energy to power a dim light bulb. Operating a supercomputer with equivalent processing capacity requires tens of thousands of times that power output. Because physical chips face hard constraints on speed and energy consumption, the timeline to AGI cannot rely on making physical processors faster. It requires a structural pivot in software architecture. Historically, AI operated on rigid sets of pre-programmed rules defining exact limitations. That approach proved too brittle to generate complex, adaptable intelligence. The field pivoted toward deep learning and reinforcement learning. These software systems mimic biological neural networks, bypassing explicit instructions to train themselves autonomously through data exposure. This bar chart displays forecasted deep learning software revenue. The commercial expansion of this algorithmic approach pushed global revenue projections from roughly $100 million in 2015 to past $10 billion by 2024. But deep learning has a distinct vulnerability. The algorithms break down rapidly and fail to generalize if they are not continuously fed massive, varied inputs of new data. To sustain this model, the AI industry relies on the parallel expansion of cloud computing to host, manage, and distribute the required volume of training data. By 2020, global cloud IP traffic was projected to hit 14.1 zettabytes annually. This infrastructure creates a digital reservoir large enough to train highly complex neural networks. This data is gathered through expanding mobile broadband penetration and billions of sensors operating within the Internet of Things, creating a continuous sensory network across the physical world. The modern path to AGI is driven by the relationship between self-training deep learning software and the effectively infinite supply of cloud data. To track the progress of these macro dryers, the IFS forecasting platform relies on task-oriented evaluations, measuring an algorithm's performance against highly specific, isolated functions. Evaluating true intelligence is complicated by the AI effect. Historically, as soon as an algorithm successfully solves a complex problem, the achievement is dismissed as a function of computing power rather than intelligence. When IBM's Deep Blue defeated chess grandmaster Garry Kasparov in 1997, it was widely reframed as a triumph of pure calculation and memory. This table outlines the specific technologies comprising the narrow AI representation in the IFS model. To establish standardized tracking, the system monitors performance across 6 specific categories: computer vision, machine learning, natural language processing, robotics, the Internet of Things, and reasoning. This chart shows the rapid growth in computer vision. Between 2010 and 2015, ImageNet classification error rates dropped from 28.2% to 6.7%, crossing the threshold of human accuracy. Parallel advancements occurred in natural language processing, allowing systems to extract, summarize, and interact using complex human text. Leading up to its Jeopardy victory in 2011, IBM Watson's response precision, the percentage of questions it chose to answer correctly, more than doubled between 2007 and 2010. In 2016, DeepMind's AlphaGo defeated top player Lee Sedol, proving that reinforcement learning could conquer complex environments that resist traditional rules-based programming. But while these benchmarks show significant improvements in isolated domains, shattering a benchmark in image recognition or board games does not automatically result in general human intelligence. The IF's forecasting platform synthesizes these disparate narrow AI benchmarks into a single mathematical projection metric. Progress across all 6 categories is assigned a machine IQ index score on a scale from 1 to 10. This number represents the aggregate capability of the entire technological spectrum. Tracking this index reveals the primary constraint holding back the forecast. The emergence of AGI is entirely constrained by the rate of improvement in machine reasoning. General reasoning is distinct from the narrow achievements we see today. Translating a language or identifying an object requires recognizing a statistical pattern. Reasoning requires understanding the context of that information. This table defines the missing elements. To progress, machines must develop common-sense reasoning to navigate ordinary situations, and they must learn to execute optimal planning under high levels of uncertainty in real-world environments. The 2050 timeline depends entirely on when researchers solve the theoretical requirements of machine reasoning. AGI is not delayed by a lack of raw processing power or cloud data infrastructure. It is constrained by the challenge of programming a machine to understand context and intent. The mechanical forecast triggers AGI availability only when the machine IQ index reaches a score of 10 across all 6 technological approaches simultaneously. Based on the current growth vectors of hardware efficiency and data generation, the model calculates that this threshold will be crossed between 2040 and 2050. Once general reasoning is achieved, the model projects a positive feedback loop. An AGI system will direct its cognitive capabilities towards its own software, accelerating future research. As the machine IQ pushes past a score of 10 and approaches superhuman levels, the IFIS projection models the arrival of superintelligent AI before the close of the 21st century. This date is a sensitive mathematical extrapolation. Alter the limits of physical hardware efficiency, or shift the timeline for algorithmic reasoning, and the arrival date of this new intelligence moves with it. The International Futures Platform is a quantitative macro-level assessment system. It models interconnected variables of global human development across 186 countries. Within this framework, forecasters have calculated a specific window. They estimate that artificial general intelligence will become available between 2040 and 2050. Tracking the same data forward, the model projects a secondary emergence, superintelligent AI, developing near the end of the current century. AGI identifies a system capable of human-level cognition and reasoning across all domains, moving past the constraints of single-task algorithms. By treating AGI as a macroeconomic variable rather than a science fiction concept, we can evaluate the quantitative data driving this timeline and use it for actionable policy planning. Benchmarking AI progress is difficult. The technology pivots rapidly, and the metrics for success constantly shift. The field also suffers from the AI effect, a behavioral bias where the moment a machine solves a highly complex problem, observers reduce the achievement to brute force computation and refuse to classify it as true intelligence. We can bypass that bias by examining the exact mathematical vectors the IF's model uses to justify its 2040 projection. The forecast relies on three converging trajectories: physical hardware limits, software architecture evolution, and measurable progress in narrow AI. For the 2040 window to hold up, these independent variables must align to produce a unified machine IQ capable of matching human cognition. This chart tracks the number of transistor components per chip. It visualizes Moore's law, the principle that processing power doubles at a regular, predictable interval. Under this model, computing capacity compounded continuously, driving decades of technological expansion. But this next graph plots processing speeds against thermal design power, revealing a different physical reality. After 2004, the maximum clock speed's upward trajectory flattens into a plateau. The maximum safe power consumption follows the exact same leveling curve over that identical period. Chip manufacturers are hitting the theoretical limits of space and physics. Attempting to scale hardware processing through brute force is becoming technologically restrictive and cost-prohibitive. Because of this physical plateau, hardware growth rates alone cannot mathematically sustain the push to AGI by 2040. To measure raw computational performance, computer scientists use FLOPs, floating point operations per second. Global hardware capacity is estimated at 1.5 times 10 to the 21st flops. The human brain sits within a similar magnitude, but the disparity is energy. A supercomputer requires the energy of 10,000 light bulbs, while the human brain requires only one. Hardware capacity is massive but inefficient. Therefore, reaching human-level intelligence depends almost entirely on how we structure the software environment running on top of it. As hardware levels off, deep learning networks and cloud computing infrastructure step in to carry the momentum. This chart shows forecasted revenue for deep learning software. The aggressive upward slope provides a market validation of neural networks. By 2024, projected software revenues crossed the $10 billion mark, driven primarily by massive investments across North America and the Asia-Pacific. Deep learning algorithms operate differently than traditional logic trees. They train themselves by processing vast, unstructured datasets. That architecture is fueled by global cloud traffic, which reached an estimated 14.1 zettabytes annually by 2020. This data density enables a shift toward reinforcement learning. Here, an AI makes active decisions, learning continuously from thousands of simulated failures. When Google's AlphaGo defeated human champion Lee Sedol, it proved that machines could master complex, intuition-heavy environments purely by learning through aggressive, continuous data trials. The scale of cloud data and self-training algorithms allow developers to maintain progress even as physical hardware scaling slows. Despite those algorithmic leaps, every system built so far remains narrow. They execute one specialized task and nothing else. This table outlines the 6 major technologies comprising the narrow AI representation within the IWEF's model. 2 of the most heavily researched pillars are computer vision and natural language processing. Progress here is steep and easily tracked. Over a 5-year span, the error rate for ImageNet computer vision classification dropped from 28.2% down to 6.7%. Natural language processing shows similar acceleration. IBM's Watson required strict benchmarking to interpret and answer complex questions. Between 2007 and 2009, Watson's response precision more than doubled, jumping from 30% accuracy up to 67% before facing human competitors. The IIF's model tracks the distinct velocities of all these benchmarks, aggregating them mathematically into a unified machine IQ score scaling from 1 to 10. But the 6th pillar is the anomaly. Reasoning, planning, and decision-making trails significantly behind the others. This lack of generalized machine reasoning acts as a structural bottleneck. It restricts the aggregate index, preventing the machine IQ score from reaching human parity.
AGI will emerge at the exact point where reinforcement learning models are fed enough cloud data to crack this specific reasoning bottleneck, pulling the sixth pillar into alignment with the other five. We can now evaluate the complete logic behind the 2040 to 2050 prediction window. The hardware scaling curve flattens out, but the software curve, driven by cloud computing and reinforcement learning, rises exponentially. Mapping the unified machine IQ index across these foundations, the score crosses the threshold of generalized human intelligence precisely between 2040 and 2050. The timeline is a mathematical intersection. It calculates exactly when algorithmic efficiency and data scale outpace the slowdown in physical hardware. Isolating this timeline gives governments and economists a definitive anchor point for structural planning. Defining AI as a numerical index allows forecasters to plug the variable into massive platforms, forcing interaction with energy grids, demographics, and financial markets. Analysts can adjust the machine IQ metric to run accelerated or delayed scenarios, testing exactly how human productivity reacts at different stages of automation. The data maps out localized labor displacement and reveals how international trade patterns will reorganize over the next 20 years. The integration of machine intelligence into the global economy is a quantifiable process. Mitigating the friction of that transition requires continuously tracking and calibrating these exact metrics against the physical data.
Current developmental metrics project that artificial general intelligence will emerge between the years 2040 and 2050. The International Futures Integrated Assessment Platform produced this window through quantitative macro-level modeling. This platform maps global human development by interconnecting datasets across 186 countries, tracking the specific relationships between agriculture, economics, energy, and technology. To understand why the math points to that specific decade, we have to look past qualitative predictions. We need to examine the exact hardware constraints, software architectures, and methodological limits that define this window. The forecast relies on decoupling AI into three distinct measurable categories. The first category is narrow AI. These specialized, task-oriented systems dominate the commercial landscape today, performing functions like image recognition and pattern matching. The second category is artificial general intelligence, or AGI. This refers to a unified system exhibiting cognitive applicability across all domains, including reasoning and planning. The third category is superintelligence, an intellect whose cognitive performance exceeds human capability in virtually every domain. Exponential progress in narrow, task-based algorithms does not guarantee a linear path to AGI. Correctly forecasting the arrival of general intelligence requires tracking specific physical drivers and distinct cognitive subdisciplines. The first major variable is hardware. Measured by Moore's law, this chart shows the stuttering progress of clock speeds and thermal design power. This divergence indicates manufacturers are approaching physical limits, forcing a plateau in processing speed. In terms of raw computational capacity, global hardware processing power, measured in flops, has technically surpassed the estimated output of the human brain. However, a significant efficiency deficit remains. A human brain operates on the energy of a dim light bulb, whereas equivalent supercomputers require exponentially more power. Because hardware scaling is reaching limits, the timeline to AGI depends on software architecture. Software development has shifted toward deep learning architectures. These bypass pre-programmed rules in favor of neural networks that learn through exposure to data. This shift is reflected in market confidence. This chart shows the forecasted revenue for software built using deep learning, rising sharply from 2015 toward 2024. Deep learning requires massive datasets, which are supplied by the rapid penetration of global cloud computing. This data pipeline is massive. Annual global cloud traffic reached 14.1 zettabytes by 2020. While deep learning focuses on pattern recognition, reinforcement learning focuses on decision-making. These systems learn through vast trial and error. In 2016, AlphaGo demonstrated this capability by defeating Grandmaster Lee Sedol, proving reinforcement learning could solve problems too complex for conventional rules-based programming. While these neural networks generate commercial value, they are currently optimizing narrow tasks. They have not yet bridged the gap to general intelligence.
Modern benchmarks use task-oriented evaluation to quantify progress. The ICEF's framework tracks narrow AI across 6 foundational and emergent technologies: computer vision, machine learning, natural language processing, robotics, and the Internet of Things. Progress in these fields has been rapid. In the ImageNet competition, visual error rates dropped from 28.2% to 6.7% in 5 years, eventually surpassing the human error threshold. Microsoft's visual recognition algorithms have already officially outperformed human error rates in standardized tests. Parallel milestones exist in natural language processing. Baidu's deep speech, for instance, has outperformed human transcription error rates in both English and Mandarin. These software breakthroughs enable physical navigation. Robotics has moved from human-controlled assembly to systems capable of crossing the finish line at the DARPA Grand Challenge. This velocity creates an illusion. Successfully completing complex, narrow tasks can look like intelligence, but it is actually hyper-specialization. Because 5 of the 6 narrow AI categories are advancing at this speed, the timeline to AGI hinges entirely on the lagging 6th category. That 6th sub-index is reasoning, planning, and decision-making. Progress here is often obscured by the AI effect. Once a machine completes a logic task, like Deep Blue winning at chess, the victory is often dismissed as computational brute force rather than true reasoning. The limitation is real. Deep learning excels at recognizing static patterns, but fractures when data environments shift unpredictably. Achieving AGI requires mastering subfields like automated deductive reasoning and common sense reasoning. Simulating a human's ability to make basic presumptions about ordinary, day-to-day situations is significantly more complex than translating text or identifying an object. This reasoning bottleneck is the mathematical anchor that pulls the AGI forecast away from the immediate present and into the 2040-2050 window. The IFES methodology unifies these disparate technological vectors into a single predictive index. The model tracks 6 narrow AI categories toward an index score of 10. Vision, language, and robotics approach their targets, while the reasoning metric lags. AGI is achieved only when reasoning catches up. At 10, they merge into a single machine IQ master score. The platform projects this moment of convergence will occur between 2040 and 2050. In the IF's framework, AGI represents the alignment of computing ceilings, neural architectures, and deductive logic. Beyond 2050, achieving AGI theoretically triggers a massive, completely unstoppable positive feedback loop of recursive self-improvement in research and investment. As machine IQ scales past superhuman limits, the model forecasts the development of true superintelligence close to the end of the century. By pinning these timelines to empirical indices, analysts can move past speculation to prepare for the impacts on global labor, trade, and economic productivity.
We're trying to pinpoint a very specific quantitative timeline, the exact decade when a machine will match human cognition across every domain. To model that timeline, researchers at the Frederick S. Pardee Center utilize the International Futures, or IF's, platform. This is an integrated assessment model that forecasts global macro-level systems out to the year 2100. The IF's model divides AI development into distinct phases. The baseline is our current era, narrow AI. These are systems strictly confined to isolated task-oriented capabilities. An algorithm can translate text or recognize a face, but it cannot apply that logic elsewhere. The next evolutionary phase in the model is general artificial intelligence, or AGI. This is a single, unified system capable of generalized, cross-domain reasoning, perception, and planning. To measure the transition from narrow tasks to general logic, the IFAB's platform introduces an index score called machine IQ, a quantitative metric roughly analogous to human IQ scoring. Tracking current technological improvement, the forecast isolates the arrival of AGI. Machine IQ is projected to reach human levels between 2040 and 2050. Once crossed, the final phase begins. The emergence of superintelligence is projected near the end of the century. This forecast is built entirely on the interaction of measurable drivers, historical transistor density, cloud IP traffic volumes,
and global R&D investment flows. The central challenge of the forecast lies in charting the jump from narrow algorithms to a generalized machine IQ. We are attempting this transition exactly as the foundational hardware drivers of the past 50 years are failing. To understand if AGI will actually arrive by 2050, we have to dissect the physical plateau hitting the microchip industry and the massive software pivot currently keeping the timeline alive. For decades, the engine of computing power was governed by a single observation, Moore's law. Proposed in 1965, it predicted that the number of transistors on a microchip would double every year. Intel co-founder Gordon Moore set the baseline for hardware scaling, pushing investment to ensure processing speeds compounded exponentially. We measure this raw computational performance in flops, floating point operations per second. By recent estimates, global computing capacity operates in the region of 10 to the 21st flops. The human brain operates anywhere from 10 to the 18th to 10 to the 25th flops. In raw mathematical speed, our top supercomputers have reached hardware parity with biological intelligence. But power is not efficiency. A human brain runs on roughly the energy required to power a single dim light bulb. The supercomputers matching that raw processing speed require enough electricity to power 10,000 of those bulbs. Now that hardware engine is stalling. Chip manufacturers are hitting the theoretical limits of atomic space and physics. This chart tracks processing speeds. Notice the data. While early decades show exponential growth, physical clock speeds flatlined since the early 2000s. While transistors per dollar rises, the maximum safe power consumption for a single chip has hit a hard physical ceiling. With localized hardware scaling effectively tapped out, the AI industry can no longer rely on faster chips to brute force the development of AGI. The 2050 timeline now depends entirely on moving processing power off the localized chip and relying on distributed infrastructure and radical shifts in software architecture. That architectural shift is deep learning. Instead of relying on raw processing speed to execute strict commands, deep learning software mimics biological neural networks. It operates without pre-programmed instructions. The software trains itself to detect patterns strictly through repeated exposure to information. To function, these neural networks require massive volumes of data. That prerequisite was only met recently, driven by the global surge in mobile broadband penetration and continuous internet connectivity. This chart shows forecasted deep learning software revenue. In 2015, the market sat near $100 million. Pushed heavily by North America and Asia Pacific, the curve exponentially rises, projecting revenue to vault past $10 billion by the mid-2020s, showing a massive pivot. To process these massive datasets, the software relies on cloud computing. Global cloud IP traffic reached nearly 4 zettabytes in 2015. By 2020, that number surged to an estimated 14.1 zettabytes, representing a massive continuous movement of digital information. Cloud architecture removes the computing burden from the individual device. A local machine no longer needs to possess the hardware capacity to execute a complex model. It accesses results computed remotely by massive server farms. This combination of deep learning software and distributed cloud infrastructure bypasses the physical limits of a single chip, providing the necessary environment for specialized narrow AI to scale. To forecast when these systems will achieve general intelligence, the IFEF's model breaks narrow AI down into 6 foundational operational categories. We track progress across 5 technical pillars: computer vision, machine learning, natural language processing, robotics, and the Internet of Things. In computer vision, image net error rates plummeted to 6.7%. In natural language processing, IBM's Watson precision more than doubled over 2 years. These systems are commercially successful, but high precision on a single task is not general intelligence. Early AI milestones relied heavily on closed, predictable environments. In 1997, IBM's Deep Blue solved a massive, complex mathematical problem to defeat a human grandmaster in chess. The defeat of Garry Kasparov proved machines could brute force logic, but only when constrained by rigid, pre-programmed rules. Moving away from pre-programmed rules requires intuitive decision-making. In 2016, a Google program called AlphaGo used reinforcement learning, learning by doing, to conquer a game with variables too vast for simple brute force calculations. AlphaGo defeated Lee Sedol a decade earlier than experts thought possible.
the machine adapted to its environment. Which brings us to the critical sixth category in the model, machine reasoning and planning. This is the bottleneck. AGI requires this final node to unify the other five. A machine must take a lesson learned in computer vision, translate it through language processing, and apply it to an unrelated problem using logic. Tracking the maturation of this specific reasoning node and pinpointing the moment it successfully fuses these disparate narrow systems determines the exact arrival date of AGI. When we return to the macro-level timeline, we map the trajectory of these 6 interconnected nodes moving forward. As machine reasoning advances, it acts as a central hub. It begins fusing visual processing, language comprehension, and robotics into a synthesized cognitive structure. The quantitative output of this convergence is tracked as a single machine IQ score. The critical threshold for general artificial intelligence is the exact coordinate where this aggregate machine intelligence intersects the baseline of human cognition. Driven by the pivot to cloud architecture and exponential deep learning investment, the ICEF's model projects this intersection will occur between 2040 and 2050. Crossing this line triggers an immediate chain reaction. It initiates a recursive positive feedback loop in research and development, where the AGI system itself can begin optimizing its own software architecture. The outcome of that recursive loop is superintelligence. Because the system can continuously improve itself without human limits, the trajectory drastically steepens. The model forecasts this level of intellect, exceeding human performance across all domains, by the end of the century. Measured, hitting these dates is entirely contingent on the underlying data. The forecast requires massive, continuous commercial investment in AI startups and a sustained expansion of global information and communication technology to feed the neural networks. Solving these specific physical, economic, and structural engineering challenges will likely define the technological landscape for the remainder of the century.
Predicting artificial general intelligence is often treated as a philosophical exercise. The IF's model frames it as a problem of rigorous macroeconomic forecasting. Researchers use the International Futures, or IF's, integrated assessment platform. This quantitative system models interconnected data across 186 countries to produce dynamic forecasts for global human development. Based on the current trajectory of its inputs, the model calculates that AGI will emerge between 2040 and 2050. Following that crossover, it projects the development of artificial superintelligence close to the year 2100. Policy analysts frequently view long-term timelines for machine intelligence as arbitrary. Predicting specific decades invites skepticism. But the IF's model produces these dates deterministically. It tracks the physical limits of hardware, capital investment, and information infrastructure to calculate the trajectory. The model builds its forecast around 3 specific variables. First, the physical constraints on computer chips. Second, the shift toward new algorithmic design. And third, the documented collapse of error rates and isolated tasks. Current technology sits within the epoch of narrow AI. These systems are highly capable, but only perform specific, isolated tasks without any general comprehension. A machine with general intelligence is not expected to appear as an unpredictable discontinuity. Its arrival is mathematically bounded by the compound improvements of our hardware and software. To validate this window, we must reverse engineer the specific data points driving the calculation. Identifying a deterministic timeline for AGI shifts the conversation. It allows planners to move past the question of whether human-level machine intelligence is possible and begin modeling the consequences of when it arrives. The first variable feeding the forecast is raw computing hardware, traditionally measured by Moore's law. This logarithmic graph maps the historical growth of computing power. It charts the doubling of transistor components on integrated circuits every year from 1959 to 1975, forming a perfectly straight line. Intel co-founder Gordon Moore identified this predictable trajectory. That exponential scaling led scientists to assume raw power would eventually allow machines to achieve human-level cognition. This chart reveals the modern reality. The lines tracking clock speed and thermal design power flatten into a plateau. Manufacturers are hitting theoretical limits of physics. Cramming more transistors generates too much heat, meaning scaling through brute force hardware is reaching its end. Despite this plateau, total global computing capacity is extensive. Current estimates place it around 2 times 10 to the 20th power floating point operations per second, or flops. That computational output puts global server capacity at the upper threshold of the power required to simulate the calculations of a human brain. The problem is energy efficiency. An organic human brain runs on the power of a single dim light bulb. A modern supercomputer processing the same volume of data requires enough energy to power 10,000 light bulbs. This creates a friction point in the model. If physical hardware is plateauing and remains inefficient, the timeline to AGI should be slowing down, yet the forecast still points to 2050. That persistent acceleration indicates the model has shifted its primary growth metric. The drive toward 2050 is no longer relying on physical transistors. It relies on self-optimizing algorithms and data architecture. To bypass the hardware ceiling, computer science required self-optimizing leaps in software architecture. For decades, programmers relied on rigid, rule-based instructions. They told machines exactly what they could and could not do. In complex, unpredictable environments, those pre-programmed rules failed. Deep learning changed the approach. Instead of following explicit coding, deep learning software mimics biological neural networks, learning to detect structures through exposure to extensive datasets. The next step is reinforcement learning.
This moves systems past pattern recognition and into decision-making. The machine performs a task thousands of times, adjusting its own behavior through a cycle of failure and feedback. The speed of this architecture was proven in 2016. A program trained via reinforcement learning bested a human grandmaster at the game of Go, a feat experts assumed was still a decade away. The IEF's platform tracks this software evolution by monitoring a visible proxy, commercial investment from technology firms. This bar chart projects global revenue for deep learning software. Between 2015 and 2024, the curve sweeps upward, projecting tens of billions in growth. This influx of capital acts as the new accelerator. Investment previously required to shrink silicon now pours directly into algorithmic efficiency. By transitioning from physical hardware scaling to self-teaching algorithms, the mathematical march toward general intelligence maintains its speed, keeping the 2050 forecast viable. Analytical, precise. These algorithms are assessed using a rigid testing framework. Today, machine intelligence is measured through task-oriented benchmarking. This table defines how the IF's model categorizes current narrow AI into 6 functional domains: computer vision, machine learning, natural language processing, robotics, the Internet of Things, and reasoning. The platform quantifies progress by tracking the documented collapse of error rates within these specific domains. We can verify this by examining the first benchmark, natural language processing. In late 2007, IBM Watson answered Jeopardy-style questions with 30% accuracy. By 2009, driven by machine learning, precision more than doubled to 67%. The second benchmark, computer vision, follows the same trajectory. At the Stanford ImageNet competition, the ability of algorithms to correctly classify objects improved by a factor of 4 in 5 years. Error rates fell from 28% to under 7%, dropping below the threshold of human error. The third benchmark tracks physical navigation and robotics. Early DARPA grand challenges ended in total failure. Just a few years later, multiple vehicles completed a 60-mile urban course, making real-time decisions. Across every category, the time required for breakthroughs is shrinking. Problems that stalled computer scientists for decades are now being solved in months. Individually, these are narrow systems, but plotted together, the simultaneous compounding collapse of their error rates forms the empirical bedrock for predicting the crossover into general intelligence. The IFIS platform pulls these isolated inputs together to finalize the forecast. It takes the physical ceiling of hardware, the influx of algorithmic capital, and the collapsing error rates of narrow tasks, and normalizes them into a single metric. That metric is the Machine IQ Index, scaled out of 10. Synthesizing all current data trajectories, the Machine IQ curve hits human equivalence within the 2040 to 2050 window. The math continues. Pushed by identical drivers, the intelligence curve reaches artificial superintelligence by 2100.
Reaching the 2050 target requires mastering the sixth most complex category, machine reasoning. Reinforcement learning is currently driving narrow systems to cross-pollinate. By learning through trial and error, algorithms are bridging the gap between identifying static patterns and executing generalized planning. The 2050 timeline is a rigidly bounded trajectory. It is dictated by capital flows, energy consumption, and the compounding improvements of deep learning networks. The arrival of AGI shifts the value add away from labor and toward capital-intensive machinery. As these systems master the vision and navigation benchmarks we've tracked, they enable the localized production of goods, altering the trade networks that once relied on exported human labor. For macro forecasters, 2050 represents a boundary where these shifting productivity and labor variables require new mathematical frameworks to map a post-AGI global economy.
To forecast the arrival of artificial general intelligence, you have to measure the trajectory of a technology that does not exist yet. The challenge is compounded by a psychological phenomenon called the AI effect. Every time engineers solve a complex cognitive problem, observers quickly reclassify the achievement as mere computation rather than actual intelligence. Mastering a game like chess or successfully identifying objects in a photograph were once viewed as the absolute peaks of machine intelligence. Today, we dismiss them as basic, everyday automation. This constantly shifting baseline creates a severe problem. You cannot use traditional qualitative methods to predict AGI if the definition of intelligence changes every time a milestone is reached. To map a real timeline, strategic forecasters have to abandon philosophical debates about what constitutes a mind. They rely instead on strict, quantifiable metrics tied to specific task execution. The International Futures, or IF's, platform is a quantitative macro-level system built to model and assess highly complex global development trends. To bypass the AI effect, IF strips away vague concepts of sentience. It breaks the ecosystem down into highly specific, measurable technology pillars. The model structures development across a timeline starting with early narrow applications in 1950, moving through the present day, and extending outward to the year 2100. Based on their current path modeling, IF's mathematically estimates that artificial general intelligence will emerge between the years 2040 and 2050. This date is derived by aggregating the historical improvement rates of narrow, task-based technologies and converting them into a unified machine IQ score. That mid-century target represents the strict mathematical intersection where the physical limits of hardware meet the measurable evolution of software. There is a pervasive assumption that exponential hardware growth will automatically brute force the arrival of AGI. Raw global computing power, measured in flops, is already nearing the estimated processing capacity of the human brain. This chart displays historical computer processing speed data. The top solid black line, representing transistor density, confirms Moore's law has historically held true, but the two lower lines for actual processing speeds and power consumption show a stark plateau beginning in the early 2000s. Chip manufacturers are approaching the theoretical limits of space and physics. Pushing raw processing speed higher is becoming highly constrained and entirely cost-prohibitive. Raw hardware scaling has hit a thermal and clock speed wall. Reaching AGI requires a structural architectural shift from hardware scaling to highly advanced software engineering. To bypass that physical bottleneck, the industry leveraged cloud computing infrastructure and oceans of big data to shift how machines operate. Rather than pre-programming machines with strict rules, developers began training algorithms. This shift yielded deep learning, a software architecture that mimics biological neural networks. By exposing the system to vast amounts of data, the machine trains itself to recognize patterns entirely on its own. That pattern recognition evolved into reinforcement learning. Here, machines learn complex decision-making by attempting a task thousands of times in a simulated environment. In 2016, a Google program trained this way defeated Lee Sedol, one of the world's top Go players. These developments establish that AGI will not emerge spontaneously from a hardware lab. It will be grown through localized, task-based algorithmic mastery. To quantify software growth, the IFUS framework categorizes the modern AI ecosystem into 6 foundational technologies: The first two axes track computer vision and machine learning. Next are natural language processing and robotics. Finally, it tracks the Internet of Things and reasoning for decision-making. The combination of performance metrics across all 6 of these distinct pillars creates an aggregate machine IQ index score. By tracking the historical progression of these specific pillars, researchers establish a quantifiable trajectory toward AGI. Forecasters map how rapidly these individual technologies improve to project when they will cross the human threshold. In machine learning, between December 2007 and late 2009, the response precision of the IBM Watson supercomputer completely doubled. In computer vision, the error rates in the Stanford ImageNet competition collapsed from over 28% to just 6.7% in exactly 5 years. In language processing, AI software successfully defeated the CAPTCHA test with 90% accuracy, breaking an authentication system designed entirely to separate humans from machines. By mathematically analyzing the speed at which error rates drop and precision performance doubles across these narrow domains, the IF system extrapolates the exact decade the aggregate machine IQ will overtake human baselines. When you chart the actual performance data, a severe disparity emerges within the model. The emergence of AGI is not delayed by vision, language, or pattern recognition. Those technologies are already expanding rapidly. The bottleneck anchoring the entire system is reasoning. True machine reasoning requires the capacity to plan, apply common sense, and make critical decisions under extreme uncertainty in unpredictable environments. Modern applications of true reasoning remain severely limited. The technology has mostly been used to assist in proving strict mathematical theorems, lacking the flexibility required for general intelligence. The forecasted 2040 to 2050 window for AGI is entirely contingent on how quickly developers can solve this specific reasoning bottleneck. If that final reasoning constraint is broken, the aggregate machine IQ score will hit human parity in the 2040s. The literature projects this will trigger a positive feedback loop. An AGI system drives its own research and development, accelerating progress beyond human comprehension. Driven by this feedback loop, the IFS model projects the advent of superintelligent AI will follow closely behind, arriving before the end of the current century. By utilizing rigid, task-based metrics rather than philosophical definitions, forecasters can cut through the commercial hype, map the physical bottlenecks, and rigorously prepare for the mid-century transition to artificial general intelligence. If we plot the timeline of human technological development across the 21st century, the critical interval arrives between 2040 and 2050. This is the window where current macroeconomic models project the emergence of artificial general intelligence, or AGI. Pinpointing a date for AGI is difficult because standard forecasting relies on vague speculation. The field also struggles with the AI effect, the tendency to reclassify automated tasks as mere computation rather than intelligence the moment they are successfully achieved. To bypass subjective definitions, researchers utilize the International Futures, or IF's, integrated assessment platform. This is a quantitative, macro-level modeling system designed to produce dynamic forecasts by tracking highly interconnected data from infrastructure and energy to education and finance across 186 countries. The IFS methodology discards abstract debates, categorizing AI into 3 operational typologies: narrow AI, general artificial intelligence, and superintelligence. The platform tracks physical drivers, hardware, software, and data infrastructure, and synthesizes them into a quantifiable machine IQ index, roughly analogous to human IQ. The forecast placing AGI in the mid-21st century is the direct output of this index. To understand how that timeline is calculated, we must deconstruct the IFS model and examine the empirical datasets driving it. The baseline for forecasting artificial intelligence begins with physical hardware. Historically, computing processing power has been defined by Moore's law, the 1965 observation that the number of transistors on a microchip doubles roughly every year, producing an exponential curve in computational capacity. Following that trajectory, current global computing hardware has already met and surpassed the theoretical computing limits of the human brain, capable of operating well beyond the estimated human maximum of 10 to the 25th power floating point operations per second. This graph displays Moore's original observation, tracking the log base 2 of transistor components against time. It establishes the strict exponential expectation that defined decades of engineering. However, physical hardware is reaching a critical bottleneck. This second chart plots decades of chip introduction dates against performance. While the raw number of transistors, the top line, continued to climb, actual clock speeds began to plateau in the early 2000s, a phenomenon the industry refers to as stuttering. The cause is visible in thermal design power limits, which flattened as manufacturers hit the theoretical limits of heat dissipation and space. As the inset graph shows, the raw cost efficiency of buying transistors per dollar completely stalled out around 2012. Pushing physical transistor density further is becoming both technically prohibitive and economically inviable. Because raw processing speed is hitting the ceiling of physics, physical hardware alone can no longer act as the primary engine for cognitive growth. Faced with flatlining hardware returns, the trajectory toward generalized intelligence requires a pivot. Progress relies on algorithmic software efficiency and distributed networks. The solution to the hardware bottleneck is deep learning. Deep learning algorithms mimic biological neural networks, training themselves to detect complex patterns through exposure to data, rather than relying on rigid, pre-programmed human instructions. This chart projects global software revenue built using deep learning. The exponential scaling across every world market over a single decade validates the massive industrial pivot toward algorithmic efficiency. Deep learning algorithms bypass local physical hardware limits, but they require vast volumes of raw information to train effectively. That demand necessitates a shift away from localized processing and toward distributed cloud computing delivered as an on-demand service. The scale of this distributed infrastructure is massive. Projections for global cloud IP traffic measure the flow of data at over 14 zettabytes per year, a capacity required to constantly feed pattern recognition algorithms. To understand the impact of this shift, consider early algorithmic milestones. In 1997, IBM's Deep Blue defeated chess grandmaster Garry Kasparov. That victory was achieved through localized brute force processing, calculating thousands of possible moves per second based on strict programming rules. Modern deep learning operates on a different axis entirely. By mining zettabyte-scale data distributed across the cloud, current systems identify correlations and patterns far beyond human perception without needing explicit instructions on how to win. The combination of rapidly scaling deep learning revenue and expanding cloud capacity forms the macroeconomic engine currently driving the IFS model.
Because the term intelligence is subjective, the IFS platform relies on task-oriented evaluation. It scores performance solely on a system's ability to complete specific, measurable outcomes. Today, 100% of current artificial intelligence applications are categorized as narrow AI. This table outlines the 6 core technology categories that serve as the building blocks for the IFS index. By assigning a score from 1 to 10 for each specific capability, the model tracks how close these specialized tools are to achieving general intelligence. The progress within these individual silos is rapid. In computer vision benchmarks, machine error rates for image classification dropped from 28% to 4.94% over a 5-year period, successfully crossing the threshold of human visual accuracy. We see parallel acceleration in natural language processing. Systems designed to recognize English and Mandarin audio now register character error rates of under 6%, accurately interpreting complex language patterns with higher fidelity than native human listeners. These specialized capabilities require a delivery mechanism. The deep technological penetration of mobile broadband and consumer smartphones operationalizes these tools, connecting billions of users to cloud-based speech and visual recognition algorithms daily. Autonomous vehicles and consumer robotics represent the physical convergence of these top-tier indicators. They successfully fuse computer vision with machine learning to navigate active environments and independently complete multi-stage mechanical tasks. Yet, no matter how efficiently these algorithms scale on their individual benchmarks, their rigid specialization keeps them trapped as narrow AI. They lack the capacity to merge their isolated skills into genuine general intelligence. The obstacle preventing that merger is isolated within the 6th pillar of the IFS matrix: reasoning, planning, and decision-making. While the other 5 indicators approach maximum index scores, This specific capability remains severely underdeveloped. General deductive reasoning is the deterministic constraint of the entire model. Until a machine can parse novel situations and independently formulate a plan without prior data, the other 5 pillars cannot unify into a functional AGI. Standard deep learning relies on pattern recognition from existing datasets. To break the reasoning bottleneck, researchers use reinforcement learning, a process where an agent learns by doing, attempting a specific task thousands of times through pure trial and error to discover successful behavior. The viability of reinforcement learning was proven when Google's AlphaGo defeated world champion Lee Sedol. The ancient game of Go is complex and non-deterministic. AlphaGo learned to make high-level strategic decisions in an environment that cannot be solved by rigid, programmed rules. Despite achieving strategic brilliance on the board, AlphaGo is entirely narrow. It cannot extrapolate its decision-making framework to play a game of checkers, let alone navigate an unpredictable physical environment. The ultimate benchmark for common-sense machine reasoning is the coffee test. A truly intelligent system must be able to enter a completely unfamiliar human home, successfully locate the kitchen, find the necessary tools, and independently brew coffee. The date researchers break the deductive reasoning bottleneck determines the arrival of AGI. The IFS model's central hypothesis: as the reasoning bottleneck opens and the 6 narrow AI indicators approach task completion scores of 10, they aggregate into a comprehensive machine IQ. This single metric tracks forward, limited only by software investment and algorithmic improvement speed. By combining current global cloud capacity, deep learning software expansion, and task-oriented evaluation benchmarks, the path forecast calculates that machine IQ will reach parity with human cognitive limits between 2040 and 2050. The arrival of AGI acts as a massive research catalyst, initiating an immediate positive feedback loop. Once an AGI system reaches human parity, biological cognitive limits are removed from the innovation cycle. The system applies its general reasoning to the optimization of its own architecture, recursively improving both its software efficiency and hardware design without human intervention. Recursive self-improvement triggers an exponential acceleration in the intelligence trajectory, yielding superintelligent systems before the century ends as cognitive limits vanish. The mathematical architecture behind superintelligence is currently being indexed through today's task-oriented data. Current integrated assessment models project a specific data-backed window for the emergence of artificial general intelligence, somewhere between the years 2040 and 2050. This timeline comes from the International Futures, or IFs, platform. It's a quantitative, macro-level assessment system used to generate dynamic forecasts for 186 countries. The IFs model calculates forecasts by mapping how global systems interact. It networks variables across agriculture, energy, economics, and technology, calculating how shifts in one sector constrain others. To forecast AGI, the platform translates this into a machine IQ index tracking human-level parity. That 2040 to 2050 window is the resulting mathematical intersection. It's the point where hardware limits, software evolution, and precise algorithmic bottlenecks finally align. To understand how the model gets to that date, we have to divide the field into 3 distinct categories. The first is narrow AI, specialized systems engineered strictly to perform one isolated task. Historically, we measure these systems through task-oriented evaluations in isolated strategic environments. Think of Garry Kasparov sitting across the chessboard in 1997. His opponent, the IBM Deep Blue supercomputer, mastered that specific environment through raw computational power. It was brute force programming, entirely devoid of general adaptability. That contrasts directly with the second category, artificial general intelligence. AGI requires a single unified system capable of exhibiting human-level reasoning across any cognitive area: language, planning, and creativity. The third category is superintelligence. This describes an intellect that greatly exceeds human cognitive performance in virtually every domain of interest. Tracking the progress between these 3 tiers is difficult due to the AI effect. Every time a machine successfully achieves a benchmark, critics strip the achievement down to its base code and redefine what constitutes true intelligence. Because those goalposts are constantly moving, macro forecasters avoid abstract philosophical debates. Instead, they track specific, quantifiable technological drivers to predict exactly when a system will achieve general capability. The foundational driver of early AI progress was computing hardware, a trajectory mapped by Moore's law. Proposed in 1965, the law observed that the number of transistors on a microchip doubled yearly, establishing a reliable exponential curve for processing capacity. You can trace that scaling directly back to early chips like the Intel C4004, where the physical boundaries of silicon first started being pushed. Today, global computing hardware has surpassed the estimated floating point operations per second of the human brain. But beneath the surface, that underlying progress is rapidly fracturing. This chart shows computer processing speeds. Notice the divergence between the top line, tracking transistors, and the lower trend lines. Clock speed flattens completely around 2004. Manufacturers hit a physical wall. As transistors packed closer, extreme heat stalled the thermal design power line. Modern supercomputers require enough energy to power 10,000 light bulbs just to function. The human brain operates on the equivalent energy of a single dim bulb. Because of this thermal plateau, raw processing speed is tapping out. Brute force hardware scaling can no longer be the primary vehicle delivering us to AGI. To bypass these physical limits, the AI sector redirected its massive capital inflows towards software architecture. The focus shifted to deep learning, software that mimics biological neural networks. Instead of following rigid rules, algorithms train themselves to detect patterns through constant exposure to data. This graph forecasts deep learning software revenue across world markets. The exponential upward curve from 2015 out to 2024 illustrates the massive capital pivot backing this specific technology. A subset of this approach is reinforcement learning. Here, algorithms develop decision-making skills by attempting a task thousands of times, slowly learning to favor the behaviors that yield success. When AlphaGo defeated champion Lee Sedol in 2016, it provided a pivotal proof of concept for this method. It showed machines could navigate a highly complex, intuitive environment previously thought untouchable by standard programming. But both deep and reinforcement learning share a critical vulnerability. They break down without vast, continuous streams of training data, making them entirely dependent on global cloud computing capacity and high internet penetration rates. The growth of global cloud networks and the aggregation of big data have replaced raw silicon scaling as the primary variables determining the arrival of AGI. This table outlines how the model tracks progress across 6 categories of narrow AI. Take computer vision. By 2015, image classification algorithms dropped their error rates below 5%, officially crossing the threshold of human error. Natural language processing, or NLP, tracks how well machines manipulate and interact using human language. We saw the acceleration in this sector when systems like IBM Watson more than doubled their precision accuracy over a 2-year period, eventually processing complex conversational clues well enough to defeat Jeopardy champions. Robotics serves as the physical manifestation of these systems. Progress here is actively benchmarked by the speed at which autonomous navigation platforms can safely react to unpredictable urban environments. These task-oriented benchmarks map an exponential curve in isolated performance. But processing an image or parsing syntax independently does not equal a generally intelligent mind. When we isolate the variables inside the IF's model, one distinct bottleneck stands out, actively preventing the leap to AGI. Of the 6 core vectors, reasoning, planning, and decision-making is severely lagging. It is the anchor dragging down the overall forecast. Modern deep learning excels at pattern recognition, but that's a completely different mechanism than true reasoning. Formulating a plan, inferring context, and adapting to unpredictable situations requires cognitive flexibility that current algorithms simply lack. Because of this, the IF's platform mathematically restricts its machine IQ output. The score is directly constrained by the slow rate of improvement in this specific reasoning node. Until generalized machine reasoning is mapped and solved, the other 5 vectors remain isolated tools. They are powerful, but they cannot independently bridge the gap to AGI. This brings us back to the macro forecast. The 2040 to 2050 window represents the calculated timeline where the advancement of reasoning algorithms is projected to finally catch up with deep learning networks and hardware capabilities. That specific convergence is the moment the global machine IQ index reaches generalized human parity. Once parity is reached, the model calculates a structural shift.
The system triggers a positive feedback loop, where AGI agents independently drive their own research. This self-driven loop radically accelerates the trajectory. The constraint of human labor is entirely removed. Following this curve, the IFAST projection anticipates the emergence of true, globally dominant superintelligent AI close to the end of the 21st century. The emergence of artificial general intelligence follows a structurally constrained macroeconomic trajectory, dictated by the limits of physics, the strategic pivot of capital, and the slow grind of reasoning. Discussions about artificial general intelligence usually default to science fiction, treating it as an event that defies standard timelines. Projecting when machines reach human-level cognition requires shifting from intuition toward data-driven systems dynamic modeling. This is the role of the International Futures, or IF's, Integrated Assessment Platform, a quantitative macro-level forecasting system used by policymakers to map interconnected global development across 186 countries. The IF's framework tracks foundational physical drivers, like hardware capacity and energy systems, while benchmarking specific software technologies to map where these systems will converge. Treating AGI as dependent on physical and economic inputs grounds the forecast in mathematical constraints. AI evolution is divided into 3 phases. Narrow AI consists of specialized systems performing single tasks, characterizing our current landscape. AGI represents a theoretical system with human-level capability across all cognitive domains. Superintelligence refers to an intellect exceeding human performance in virtually all domains. Modeling the leap from narrow systems to AGI requires tracking the specific physical and network constraints that power these distinct phases. Moore's law, the observation that transistor counts on a microchip double every year, served as the historical engine of AI development. This chart shows the exponential growth of computing capacity since the 1950s. On a raw computational basis, global hardware processing power has likely surpassed the calculation speed of the human brain, measured in floating point operations per second. We are approaching the thermal limits of silicon microchips. This data shows the specific point where clock speed and thermal design power curves began to flatten. While transistor counts continue to grow, the practical processing speed of chips has plateaued. There is also an efficiency gap. The human brain operates on the energy required for a dim light bulb, whereas a supercomputer performing equivalent tasks requires enough power for 10,000 bulbs. With hardware clock speeds plateauing, the continued growth of modern AI relies on shifts in architecture and efficiency rather than raw serial processing power alone. To bypass the limitations of hardware speed, the industry shifted towards software architecture optimization. This shift popularized deep learning, software capable of mimicking neural networks to detect patterns through exposure to data, rather than relying on pre-programmed instructions. This forecast shows revenue from deep learning software growing from approximately $100 million in 2015 to an estimated $10 billion by 2024. Deep learning software requires vast data availability, which is enabled by global mobile broadband penetration. Global cloud traffic, projected to reach 14 zettabytes annually by 2020, serves as the primary training fuel for these algorithms. This decoupling of AI capability from raw hardware limits defines the model's logic. AGI development is a function of network scale and data optimization. These economic drivers allow the IF's framework to categorize and track specific AI technologies in development. The model deconstructs today's AI into 6 pillars. Computer vision and natural language processing mimic human perception and communication, allowing machines to identify images and process language. Robotics and the Internet of Things facilitate physical interaction, connecting digital calculations to real-world actions. Machine learning acts as the pattern recognition engine driving industry adoption. These domains currently operate in silos, optimizing independently without sharing a unified cognitive framework. Progress within one isolated pillar does not translate into generalized intelligence across the others. Modelers quantify progress within these pillars using task-oriented benchmarking. In 2015, image recognition algorithms reached an error rate of 4.94%, dropping below the human error threshold. In complex game environments, reinforcement learning allowed programs like AlphaGo to master variables that cannot be solved by conventional programming.
IBM's Watson achieved breakthroughs in natural language processing, doubling its precision in answering complex questions on the Jeopardy stage. These milestones often trigger the AI effect, a phenomenon where solving a complex problem is dismissed as mere computation rather than true intelligence. From a modeling perspective, these are localized optimizations of specific software functions. Superhuman performance in strictly bounded tasks can create the illusion of general intelligence without yielding a generalizable intellect. Examining the relative progress of the 6 pillars identifies the specific constraint on AGI development. This is the machine reasoning pillar, which includes planning and decision-making. Reasoning requires the ability to act in unpredictable environments without clear rules, a capability that lags significantly behind pattern recognition. The emergence of AGI is bottlenecked by the rate of improvement in this specific domain. Until machine reasoning catches up to the scale of computer vision and machine learning, AGI remains mathematically out of reach. The primary output of the IFF's forecasting framework is the Machine IQ Index. This index models the horizontal synthesis of all 6 pillars into a unified reasoning system. The score is structured to be roughly analogous to human IQ scores for benchmarking purposes. Based on current data availability and narrow benchmarking, the IFF's forecast estimates AGI will appear between 2040 and 2050. As scores approach superhuman levels, the model projects the development of superintelligent AI close to the end of the century. In the IFRAF's framework, AGI is the mathematical convergence of hardware infrastructure, localized algorithms, and global network scale. The International Futures Integrated Assessment Platform produces dynamic forecasts for 186 countries. Within this framework, a series of AI indices project the emergence of artificial general intelligence between 2040 and 2050. We can reverse engineer this specific window by isolating the quantitative inputs, like physical hardware limits, global data infrastructure, and rapidly accelerating investment velocity, that the IF's platform uses to drive the timeline. This scorecast tracks the cascading effects of current technological drivers. It treats intelligence as a measurable output of global human development, agriculture, and economics. When these macro-level trajectories are mapped out, the 2040 horizon emerges as a specific mathematical probability based on the current rate of technological improvement. The model operates across 3 distinct stages. We currently inhabit the era of narrow AI, characterized by specialized systems like Siri or Google Translate that are strictly constrained to single-task domains. The target threshold is General Artificial Intelligence, or AGI. This represents a single system capable of cross-domain cognitive performance, matching human intelligence in reasoning, planning, and creativity. Beyond AGI lies superintelligence, a theoretical intellect that vastly exceeds human cognitive capacity across virtually all domains of interest simultaneously. Since AGI does not yet exist, its arrival must be calculated by measuring the velocity of our current narrow technologies and the physical constraints of the systems that power them. Global computing capacity is already immense, with estimates ranging as high as 10 to the 21st power flops. By some raw computational metrics, our hardware already matches or exceeds the processing power of the human brain. The historical driver of this power was Moore's law. As shown here, the number of transistor components per chip doubled almost every year between 1959 and 1975, creating a trajectory of exponential growth. However, the trend line for computer processing speeds flattens after the early 2000s. Chip manufacturers are approaching theoretical limits. This plateau indicates raw processing speed is reaching an inflection point. On-chip hardware alone cannot provide the exponential jump required to cross the AGI threshold. Because local hardware is reaching these physical limits, the IFS model looks to a structural workaround, the expansion of distributed infrastructure. This shift toward distributed architecture bypasses the thermal and physical constraints of a single chip by spreading the computational load across a global network. Global cloud IP traffic will grow at a 30% annual rate, creating a massive interconnected dataset environment that didn't exist in previous decades. This network infrastructure provides the scale for machine learning frameworks to train on vast amounts of user data. Cloud computing serves as the physical bridge, linking our plateauing local hardware to the massive data requirements needed for advanced intelligence. Software is undergoing a parallel shift away from rigid, pre-programmed rules. Instead, researchers are building systems designed for learning by doing. Deep learning and reinforcement learning allow machines to improve their own performance through repeated exposure to data, effectively teaching themselves to recognize patterns and make decisions. This shift is validated by capital. Deep learning software revenue leaps from $100 million in 2015 to a projected $10 billion by 2024. This creates a feedback loop, funding talent acquisition and accelerating algorithm optimization. Algorithmic efficiency, fueled by this capital and supported by the cloud, has replaced Moore's law as the primary engine driving toward AGI. To ground this in data, the IFS model has to quantitatively index progress toward a technology that does not yet exist. The solution is to track error rate compression across narrow subdomains. By measuring how fast machines are eliminating mistakes in specific tasks, the model projects a convergence point with human capability. In the Stanford ImageNet competition, the error rate for image classification fell from 28.2 to 6.7% in just 5 years, surpassing the human error threshold. Similar scaling is happening in language processing and facial recognition, trending aggressively toward a zero-error baseline. The IFS model aggregates these disparate benchmarks into a single machine IQ proxy. This score objectively measures the closing gap between current software and baseline human intelligence. When we return to our timeline, we can now populate it with our operationalized variables: hardware limits, cloud scale, and error compression. The machine IQ trajectory, driven by algorithmic efficiencies, rises until it intersects the human IQ baseline between 2040 and 2050. This intersection represents the point where narrow capabilities in vision, language, and reasoning generalize sufficiently to match baseline human cognitive performance. The 2040 horizon represents the mathematical culmination of distributed cloud power and self-learning algorithms overcoming the physical limitations of our hardware. Crossing this AGI threshold changes the nature of technological development. When a machine matches human-level reasoning, it can be applied to the very tasks that created it. This allows the AGI to enter a recursive loop, applying generalized reasoning to optimize its own codebase and hardware at speeds no human could match. As this algorithmic feedback loop accelerates, the trajectory of machine intelligence continues to climb through the end of the century. Within the IFS model, the 2040 AGI forecast serves as the trigger point for the rapid emergence of superintelligent AI.